Hello. Good morning, everyone. Professor Alcaraz, Royos, Agostinho, please. Just a minute. Bom dia a todos. Good morning, everyone. As the Vice Director of São Carlos Institute of Physics, it's my pleasure to welcome you all for the 4th edition of the workshop on statistical mechanics. It's an honor to our institute to host this event, which besides discussing the latest developments on this field, also deservedly honors Professor Alcaraz. We thank Professor Royos and organizing committee, and also the speakers, presenters, and all the participants. I wish you all a great and productive workshop. So let's start.
You say it's working, right? Yeah. Okay, so good morning, everybody. It's first of all a great pleasure and great honor to be here and to open this workshop in honor of Chico Alcaraz. Chico is, I have not to say, you know very well, he's an extremely clever man, extremely smart, extremely deep, but on top of that, has a human touch which is really peculiar. And this is something, when you have this blend, which make a person unique. And this is why I like you so much. I'm so honored to share friendship with you. So for this reason, I'm really, it's a pleasure to open this workshop, to dedicate this talk to Chico, and I hope you will gonna like it. So the title is a bit misleading, I have to say, namely hide a lot behind the carpet, but let me keep to this. Now, what I want to put your attention on is a sentence by Richard Feynman, who said that no matter how beautiful your idea could be, no matter how creative and smart you could be, whatever you've done, if it doesn't agree with experiment, you are wrong. I mean, he's pointing out that physics is physics, it's not mathematics. It's something that pretends to talk to reality. So we have to face this issue. Now, the field of integrable models, where in a way or another, many of us works and has worked in recent years and decades, finally, which is a beautiful mathematical subject in itself, has recently have a very dramatic development. Namely, there has been a very stunning delight matching between theoretical finding and experiments that people have set up, either in cold atom, quantum spin chain, and so on and so forth. So this is really the beauty of the things. And let me take you a remarkable example, the two-dimensional Ising model in a magnetic field in 1 + 1 dimension, and its underlying E8 structure, which is one of the most beautiful Lie algebra and set of vectors that you might imagine. Now, this subject has been developed, first of all, through a beautiful and outstanding seminal work by Sasha Zamolodchikov, who point out to us that if you look at the model in the right way, namely in the scaling limit, it appears made of a bunch of particles, 8 of them, which make elastic scattering, and each particle is bound state of someone else. Now, this is the on-shell theory. The off-shell theory, namely the exact calculation of the matrix element of the quantum spin operator, has been exactly worked out in this paper that I did together with Aldo Delfino. Now, this, of course, is the starting point, is the basic things under which this paper is made of. But if you want to compare with experiment, this is what you need, the second paper. Because you have to have correlation function. Correlation functions are off-shell quantities. Now, this, the confirmation of this theory has been pursued since many years, first in Oxford, the group of Tennant and Koldea, and they got the first indication of these particles. So this was the original paper published at that time. But more recently, I've been involved in theoretical and experimental collaboration with a group of people in Shanghai that has cleverly designed a chain that belonged to this class of universality, and they were able to measure this correlation function. Now, I cannot go in detail in all this stuff, but I just want to show this one. So this is just the Fourier transform of the two-point correlation function, the magnetization, at zero momentum explores function of the energy. So this is done through typical scattering experiments. And you know, the dot are the experimental data, and what is in top is the theoretical curve. And there is no fit. It's not a best fit. The only parameter that you have to match the two is the relation between the mass gap of the theory with the magnetic field. Nothing else. So you have no parachute. So either you are wrong or right. So this gives confidence that things are really going very well. Now, if possible, I would like to convince you that there is a classical universality even richer and more intriguing than the Ising model in a magnetic field. And this is the one of the tricritical Ising model. I'm going to show you that this model has inside a lot of beautiful symmetry, like E7, in Ising was E8. Supersymmetric, duality, parity, and so on and so forth. So it's really a delightful playground to have a lot of theoretical idea, put in action, and see what's going on the experimental side. And indeed, from the experimental side, you will see that also poses a very interesting and engaging, challenging to realize this. I will argue why it's not so easy to do as an Ising model. And this is really something that the experimentalists like, is really some new challenge that you have to. So what I'm going to talk first, first I will describe you the classical universality of this model, belonging to the spin one physics, then the conformal field theory, which is underlying this, and then the symmetries I was talking about. Then I will focus, just for time and just because it's probably the most significant example, on the thermal deformation of this model, which indeed is the one which show up this E7 particle, which however can be realized as kink or particle. This didn't happen in Ising. And then I'm going to talk about how you can compute the matrix element exactly of this model and how you can construct this dynamical structure function. Okay, so I'm talking about physics of spin 1, not spin 1/2. So spin 1, of course, has also the 0 states. that you might interpret as vacancy. Namely, if you have a spin 1, you might say 1 and minus 1 is like play the role of ordinary spin, just renormalize, it's the 1/2 1. But 0 means nothing is there, okay? Is how you want to interpret. Now, this has some quantum Hamiltonian that you can construct directly with these operators. However, is much more, to say, pedagogical to present the model from the classical point of view, namely as a two-dimensional classical statistical mechanics. So from this point of view, the physics is the following, and it's called Bloom-Capell. You have as a statistical variable at each site the spin, plus and minus 1, and then an additional variable that take value 0 and 1, which tell us if the site is occupied or not. Now, both of them are dynamical. So it means a typical configuration of the system will have many sites which are not occupied, okay? Depending on the chemical potential of this variable. So the Hamiltonian you can write down in terms of these variables, probably the most general one, is the one which involves 4 coupling constants. Namely, there is a term which is like Ising type, because if 2 next neighborhood sites are occupied, TR1, then this is like sigma I, sigma j. Otherwise, if they are not occupied, they don't care. Then there is the chemical potential associated to the vacancy, and then there are 2 odd operators, which with the possibility of vacancies, there is much more way of constructing a Z2 odd spin than the usual one. Indeed, in this model, we will have magnetization as subleading magnetization. Okay, so the phase diagram of this model that you can study, say, numerically, and this has been done in the past, once you put the magnetic fields to 0, you have to look where are the critical point and the Z2 subspaces. And the phase diagram is like this. There is a first order critical line which met a second order critical line at a very specific point, which is the 3 critical points. So this is why the model is called 3 critical, because first order line met a second order. And this is the model we are talking about when we are at criticality, meaning that you have to adjust not only the coupling of the spin, but also not only the coupling of the spin, but also the chemical potential of the vacancies. All are fluctuating at the same time. Now, these lines separate low temperature phase of the model by high temperature. And actually, these 2 things are mapped by duality. So this is what I meant duality. There is an exact mapping between what's going on here and there, and that I will look later. Now, you might ask, what is the ending point of the second order line? You can argue in a very simple way that has to be Ising model. And the easiest way you can argue is like this. Imagine you start from the critical point, and then I start varying the chemical potential where I fill all the vacancies. But at the same time, I adjust my temperature. So what is the end of this transformation? The system is still critical, completely filled, is Ising. It cannot be anything else, okay? So so the final conclusion of this argument is that there is a well-defined mapping from this model to the Ising model, which actually I explore in different papers. And this is amazing because you can see really how mapping of infinite number of operators goes one into the other, and it's pretty remarkable. Now, what is the physics short distance of this model? So, conceptually, what you have to do is, starting from the lattice model, taking a continuum limit, some scaling limit, and look what are the degrees of freedom which are there. Now, short distance, Belavin, Polegov, and Zavalogikov told us, look the conformal models. And then you have to find the classical universality in one of these models. Indeed, they classify this space in of theories in low dimension, and then there is the critical point of easing, the critical point of the three-critical easing, and so on and so forth. And each of these points has its own instability, means the number of relevant operators which can bring you outside the criticality. Now, if you do this exercise, what you have to do is look the operator pro expansion of the stress energy tensor, expand in mode, and reduce essentially the problem mathematically to find a reducible representation of this algebra. Okay? So the problem has become clearly shaped. C is a parameter which identifies the classic universality, and all the operators you are dreaming to control are just those which are eigenvalues of L0, and these numbers is what they are the anomalous dimension. So the rule of the game are net and clear. Might be difficult, but this is what you have to do. Now, if you do for this three-critical easing model, the result is this. The central charge is 7/10, and this is the bunch of numbers which are the delta, the anomalous dimension I was talking about. So you can combine them. This, of course, is very skeleton, putting the analytic and anti-analytic part, constructing fields which has the scaling dimension. So we have 4 of them which are relevant. Namely, each delta is less than 1. Then there is, of course, the identity, and then there is 2 fields which are fermions, because the difference between the left and right part is half integers. So they are fermions, okay? So this theory has, even though we didn't put it, has fermion degrees of freedom in it. Now, the story starts to become pretty intriguing when you work it out, the fusion rule, namely how these fields at short distance fuse themselves and producing something else. So this is dictated by operator pro expansion and structure constant, which is like Lebesgue-Gordon. Now, what is remarkable is that if you compute them exactly, as I did, and is here the result, you notice something absolutely striking, that the operator pro expansion of the energy fields and the operator pro expansion of the density has the same structure constant. This phenomena never happened with no other statistical models, okay? So something weird is going on, but this is the signal. The signal that behind this model should have enlarged symmetry, which explains this coincidence. And what it is first of all, duality, and second, supersymmetry. Now, the 2 things are related to each other. So let me explain why. Duality is the fact that you have order and disorder operators. Namely, in high temperature, the expectation value of the order parameter are 0. On the other hand, the low temperature are different from 0. Now, as Kadanov and Cheva and many others show for easy model, there exists another operator, non-local with respect to this, which has exactly the reverse things. Has expectation value in high temperature and no expectation value in low temperature. Now, when this happened, you might have a one-to-one mapping between the 2. Okay, now, I can show that in the three-critical easing model, each order operator is going to be accompanied by a dual operator tau of equal conformal dimension. It's necessity. How to say? It's principle necessity. Has to be like this. Cannot be anything else. And I'm going to argue that this is the case because as in easing, this is consequences of the fermionic fields. Now, you can look at duality of easing model in many different ways, but the most elegant one is if you use Majorana fermions, okay? So here I want to do exactly the same. Indeed, using the field G that I introduced before, this field satisfies this operator pro expansion, and if you expand in mode, you have what? you have a beautiful supersymmetry. So together with the scaling invariance of conformal theory, you have also supersymmetry, superconformal invariance, and the irreducible representation of this algebra fall in two categories. Superfield, which means where the fermionic fields are periodic, and Ramon fields. So in superfield, you immediately can organize epsilon and t in a unique object. And this explains why the structure constants were exactly the same. Because it's like a Wigner record. The same objects share the same constant. But in the Ramon sector, the G square, which is really the supersymmetry operator of this model, is related to L0 in this way. Since in the model there is never a field whose eigenvalues delta is equal to C over 24, G square is never 0. So this means that if you apply G0 to sigma, you're going to get another field different from the previous one, but with the same anomalous dimension. And vice versa, apply G0 to tau, you're going to get back the other one. So this field has to be doublet necessarily with the same anomalous dimension. And the same is true also for the multicritical one. Now this model has symmetries, Z2 symmetry, which are the spin one, the usual one, and this Cramer one-year duality, under which the energy is odd operator and vacancy is an even operator. And notice that indeed this goes in sigma goes to tau and so on and so forth. Now this model is even more, has some hidden symmetry. Alias is like Basel in Switzerland, is the town we share Germany, Switzerland and France, okay? So this model has three critical, is nomen omen. So even the nomen itself is the crossing point of several symmetries. Indeed, this model can be realized in terms of SU2, E7, and supersymmetry. So let me show you how to do it. This is done by a theoretical construction that in conformal field theory is called coset. Coset means that you construct Versumino-Witten model on this group with certain rank, you compose them, and you coset. And once you do this, these three different cosets give rise to the same result, the same. So what happened is absolutely remarkable. At the critical point, you have the choice to choose which one you like it. But when you go away from criticality, using one field, it's like each of these symmetries has its own dog. So if you come up with one model, you excite SU2 degrees of freedom. You come up with another one, you excite D7. You come up with the other one, you excite supersymmetry. Okay? So at the critical point, they live together. But you start appreciating one from the other only when you go away from criticality. Okay, so let me just tell you roughly what is the physics of this model using just one of them. So I'm not going to justify what I'm going to say, I'm just reporting how to say what is the situation. So imagine that I use the SU2 language. In this SU2 language, all the conformal fields are essentially power of Landau-Ginzburg, okay? So I can use a Landau-Ginzburg language to understand what's going on if I switch on one of these coupling. And the result is the following. If I switch on the magnetic field, essentially is the only perturbation which is not integrable in this scenario. When I switch on the energy, the temperature, I have in high temperature particle and low temperature kinks, and this is the E7 degrees of freedom. When I switch on G3, namely a subleading magnetization, is integrable and has asymmetric kink, absolutely remarkable theory. And if I switch on the vacancy, this is where I observe supersymmetry, okay? That can be realized exactly or spontaneously broken, depending how you do it. Okay, so this is what's going on. So if I come back to the diagram, I can interpret the diagram like this is the line of unbroken supersymmetry, the first order one. This is the line of broken supersymmetry. And you remember when a supersymmetry is broken, should be massless Goldstino, which are Majorana fermions. What is this? The fermions of Ising. Okay? So you interpret the Majorana fermion of Ising as coming from a spontaneous symmetry breaking of supersymmetry. And moving in the other direction, you are excited, there is 7 degrees of freedom. So I could describe what's going on in the thing starting from exact supersymmetry, adding temperature, I move the vacuum. More I move, I become symmetric one. Then I start flattening the vacuum, then become completely flattened because it's massless. Then I start exciting new vacua like this and like this. So it's absolutely fascinating to follow how the spectrum evolve moving in this plane. I've done this job. I'm not going to report here. What I'm going to report here is what's going on only if I move in these ways. Okay? But I'm telling you, theory allows us really to understand what's going on moving in this plane and see how these particles rearrange themselves. So in this way, this is the 7 line. You can have high temperature, where you have a unique vacuum and particle above it, or you might have spontaneous symmetry breaking, where there are kink and probably bound state of them. Now, duality tells us that the odd particle here has to be the kink, while the even particle has to be the particle in both ways. Okay? This is how duality works. Okay, now, this is indeed the 7 symmetry. If you use E7, making away from criticality, you complete the diagram of E7 with the affine E7. And when you usually do this, you require extra symmetry. In this case, it's Z2 symmetry. Okay? So indeed, you see the diagram has become completely symmetric, and there is an automorphism between these things. So, okay, so you want to work it out the S matrix. So the S matrix was worked out long ago by myself and Christe, and based on the following fact. You can prove that this theory has an infinite number of conservation laws which follow a very remarkable pattern. So this spin here take values 1, 5, 7, 9, 11, 13, 17, modulus 18. There are infinite number of them. And you know what they are they? These are the Coxeter exponent of E7. Okay? So everything is matching perfectly. Based on this, you can make a very educated guess. This is how we compute the S matrix. You could say, given this conservation law, they are compatible with these microscopic ansatz. There is a fundamental particle that make a bound states, which I call A2, but can also make a second bound state, A4. You can make these ansatz. This is what the conservation law tell you. And imposing them, imposing means conservation law is to be true here and here, because it's the same. What you get is that you get that this particle, A2, should have a very well-defined mass ratio with respect to M1. Okay? So these numbers are fixed. It's like you are playing with triangle. Once you have these answers, of course you can pose immediately what is the expression of the S matrix, because I know where the pole of these guys are. So this is what we did. And once we have this as a starting point, what you use bootstrap equations. What are bootstrap? Bootstrap equations refer to the famous Orwell sentence. They say all particles are equal except one, which is more equal than the other. And what is it? The lowest one. So you can use recursive equations to compute iteratively all the remaining amplitudes. So I start with some S matrix here. I know I can compute this other one. Just pushing this line and apply Yang-Baxter essentially. So this gives rise to a non-linear way of computing this matrix. So this can be done, and this, at the end of the day, you end up with 28 amplitudes. There are many of them. There are 7 particles which appear in all possible poles of these amplitudes. There is the T channel, S channel. Now, these guys is to satisfy unitarity, crossing, and so on and so forth. So I have no time to describe in detail, but this is pretty elementary. And the pole structure gives us the bound states. Now, the bound states give us the mass. So at the end of the day, I can construct all the masses of these 7 particles because, as I told you, it's like triangle, playing with triangles. So at the end of the day, completing this program, I have all the masses of this particle except the first one, which is arbitrary, because I can only compute mass ratio. And this depends on the temperature, but all the mass ratio are fixed. And amazingly enough, these particles sit in all the diagram of DC7, okay? So notice that these of 7 particles, 4 of them are stable, namely their mass is less than twice the threshold, but some of them are in the continuum. So they are there only for integrability. So what is the structure of bound states? Well, you have to look just the pole of these amplitudes. So in 1, 1, you find pole associated particle 1 and 4, and so on and so forth. You can complete all this story. And so you have under your eyes all the scattering theory of the things. Okay, now, so this is the prediction that in high temperature I should have all these 7 particles. In low temperature, I should have 4 particles and 3 kings, okay? Now, you might say, all this is dreams. You have done beautiful exercise, but how do you know I can check. Because the way I can do, so this is the mass, the particle, what become king, low temperature, high temperature, and so on. The way I can check is I can set up a very efficient numerical method to diagonalize my quantum Hamiltonian. That has nothing to do with this matrix I've done. So you can compute this Hamiltonian. I have no time now to explain the details, but going sufficiently high in the number of states, I can diagonalize on a finite cylinder. And then depend on the boundary condition if I can look kink or just neutral particle. So look what's going on. So when I go to high temperature and I do this exercise, these are the spectrum. And I have to look the mass for very large value of the volume. And look what it is. So there is one particle 1, one particle 1.288, 1.87, 1. Exactly by spectrum. Okay? So I have a way to check this one. Now you can ask, what happens if I go low temperature? Because some of these particles should disappear because they are kinks. Is it true? When you go to low temperature, means I swap the sign of my Hamiltonian. Look what's going on. All the odd line smash to the even one and disappear and remain just the neutral part of the spectrum. Okay? So perfect, absolutely perfect. So no doubt that the on-shell theory is the right one. Then remain how to do the correlators. Now the correlators, I'm going to use the so-called spectral representation. Namely, I insert a complete set of states, which are biparticles, and I decompose by correlators in terms of a series. Series that graphically is something like this. And if you do the Fourier transform, you get the so-called dynamical structure function that can be compared with experiments. So what remains to be done is to complete this to compute this matrix element of the operators on the set of particles I have. Okay? So this is the so-called form factors. Now, this work has been done with a set of collaborators whose name is here. This paper was published, I think, last year, and take long because the structure is pretty articulated to do. So let me tell you in a brief how you compute this object exactly. So this object you can depict like this. There is a field which out of the vacuum create a bunch of particles. Now this matrix element has a lot of properties that you can explore using what I call a masochistic approach. The masochistic approach is this. You have this matrix element, say, on the in states. But then I can insert out states here as a complete set of states. Yeah. So at this point, you convert a simple object into an infinite number of objects which looks like this. The original one, you write as an infinite number of this other one with coefficient which is the S matrix. So for that reason I call masochistic. You start with something simple, you end up with something completely. However, when the theory is integrable, all these series cut down except the elastic amplitude. And when you have done this reduces drastically, and you get, you know what, you have a beautiful equation, which is a Riemann-Hilbert problem, that you can solve by Fourier transform and just looking all the singularity of these matrices. So I do not have time now to tell you how you do this job, but this can be done exactly. Then you have many ways of checking what's going on, that everything is. Now let me go to the point. Imagine I've done this on my theoretical desk, now to compare with the experiments. Now what's going on is that the lattice variables that people can measure in lab, in this model is going to be combination of the two odd operators. You are not able to distinguish a priori. So you have to fix this coefficient A and B in order to compare. So let's say this is the experimental part. So it's going to be a combination of the correlation function I've been computing with a priori two unknown parameters A and B. But remember, I have many bound states. I can go many channels, and this identity is always to be true. So this means I have at least, I don't know, many channels to fix A and B and consistently check that is done properly. And this is what happens. So you can fix it. You can fix it uniquely, and you can compute these things exactly. So at this point, you have everything you want to compare. So if you go low temperature, you have a bunch of particles that can appear. And I want to stress that the spectroscopy of this theory is amazingly rich, because you have many peaks of resonance depending how you combine the masses. So when you do this calculation, so I'm almost finished, so you can end up really with curve and give to the experimental friends, say, look, this is what you should observe here. If you go higher or if you go high temperature, the duality tell you how these guys move and the height, because everything is fixed, is exact. There is no other things. So when you do the two particle states, you're going to be, sorry, this was also the tree of term, the term of this. So this is how the contribution of the various particles enter, computed exactly. When you go to the two particles, you have just to make integrals. And then you produce these figures, which once again are exact. And in principle, in lab, you can measure this peak, where they appear, what is the shape of this curve, and so on and so forth. So this can be done low temperature, high temperature, and so on and so forth. And so let me then jump to the conclusions. So what is the overall perspective and challenge? Well, the physics of spin 1, I hope to convince you that has much richer symmetry than the easy model in itself. There are symmetry like E7, supersymmetry, duality, and this and that. So this is really an ideal playground and is a theoretical gem in itself, the model, because you can see in play, conformal field theory, quantum integrability, and all the stuff. The self-duality is related to fermions, which in this case are interacting. In Ising are Majorana free fermions, here are highly interacting. The detailed study of E7 produced all these results, the exact calculation structure function, and is a challenge to realize this system, because with spin 1/2, you have just magnetic field to do it. But spin 1, which has also the zero you cannot control magnetically. So I've been discussing with experimentalists like Oldea or others how to really do this Hamiltonian. And it's not easy, and it's something undergoing as a discussion, because you have what is called crystal field. Probably you have to squeeze the crystal to realize something. But it's a challenge, and I think it's a good challenge, how to say. It's something that can open up really and display all this symmetry, and in my opinion, is worth doing. So you see, sharp, 45. Chico, congratulations again, and happy birthday. Okay. Yeah.
Thanks, Giuseppe, for this very highly symmetric talk. Questions, criticism, comments? Well, maybe I have one. I always found amazing that the E7 group is there. And I was wondering if other of these exquisite group, I don't know the exact terminology, appears in other famous models in statistical methods.
Yeah, there is a rule of thumb numerically, very phenomenological one, which says if you take the central charge of the model and the anomalous dimension of the field you are perturbing, make the ratio. So this is 1/2, you deform by 1/16 is 8. 7/10, you define by 1/10 is 7. You take the other one is 6/7, you deform by 1/7 is 6. So this model has E8, E7, E6. And the next one is Potts model. But this is just numerology. The deep reason is that at the conformal field theory level, you have this way of playing with coset. It's pretty counterintuitive. Nobody would have ever suspected Ising as E8 symmetry, as well this model E7. Come up as a surprise. But when you see, the mathematics is absolutely solid and has to do with reduction of group. So macroscopically, you have no idea why it comes from. Only from the scaling limit, this symmetry emerge. Yeah.
Well, looking now modular invariance. So we know that we have two solutions for this.
No, in this only one. No, for Potts we have two.
But for the three critical?
No, you have only one.
RSOS is the same?
The same.
They appear also spinors there?
Absolutely. I mean, you have to find in the lattice version.
Yeah, but I understood that they don't have spins there, do they? Like you have here.
No, I mean, look, Ising, tricritical
Yes.
are the ones where the modular invariance is only 1. When you arrive to m equal 6, then you have 2.
Yeah.
You might have a pentacritical Ising or Potts model, and then you have 2 choices.
So here they are the same.
Here is absolutely only 1. Yeah. Look, I mean, I've been discussed a lot with Nienois, which is absolutely fond of this. What can I say? I mean, this is what emerged from the continuum scaling limit of the theory. On the lattice, I think should be there, but how to pick it up, I don't know. Yeah.
A bit more technical question. So you said you diagonalize this E7 for, I mean, you have some energy as a function of R graph there. So you said you did diagonalization of the model?
Sorry, I didn't get it.
So you kind of diagonalize the model, right? The E7 at some point.
Yeah. I
so
completely.
What kind of, I mean, what system size you managed to do that?
Okay, yeah.
But I mean, curious about that. So.
You mean the numerical part, the Hamiltonian? Yeah. Okay, so let me tell you.
How far could you go?
So the rule of the game is you take the conformal field theory, the states of conformal field theory, you define by the operator I'm interested in, and you compute the matrix element using the structure constant of the conformal field theory, okay? So it's a completely alternative way. There's nothing to do with the S matrix. Now, this depends on the size, R. I put on a cylinder. Now, you see immediately that the only relevant scale is M, lowest mass gap, times R. Now, you fix M, which depends on the coupling, and actually there is an exact relation between the two. I can pin down precisely. And then you go R sufficiently large. I think here I went something like 10 times M minus 1, so 10 times the correlation length. And this point, the curve, so look what you expect as a generic behavior of the curve. You should expect something like this, in which asymptotically has to be linear with mass gap, but here should be conformal invariant. So this is dictated by the correlation length, which is the mass gap. So when you do this, you see I'm here. You see here already is the mass gap. So here I'm going probably, 30 times. Depend on how many states. If you put many states, you can go larger as you want. If you put less, you have to squeeze it, okay? I think this simulation was done with around probably 300 states, something.
Okay. Next question. Yeah, thanks for a very nice talk. I was just wanted to ask you an unfair question, whether you could tell us a bit more about how they experimentally plan to realize this.
Yeah. You put the finger in the wrong place. Look, the way to get out to your question is that I'm a theoretical physicist and they have to do it. So I don't know. I've been discussing it a lot with people involved in this kind of neutron scattering data, radio frequencies, and so on. They have really no killing idea so far. Because they say, I mean, I'm reporting what Coldea told me once, discussed that the way of squeeze is like you have to not only apply magnetic field, but also squeeze in the crystal in such a way that you create an asymmetric fields. But honestly, I don't know. I've been heard another very interesting suggestion, although for me is not, probably is not the right one, to use Rydberg atoms. Because IFSC prove, I don't know if you were in the paper or not, that there is a renormalization group flow where you start from Fermi, put in quartic interaction, go very high, you follow the RG flow back forward, and you reach tricriticality, okay? And this you can do by Rydberg atom. However, in my opinion, this will not work because I'm not to reach the critical point. I have to go out. I don't know. We'll see. Experimentalists are smarter than us, so they probably will realize sooner or later. So, yeah.
Okay. Any more questions? I have to move on, so let's thank Giuseppe again.
Yeah.
So the next talk should be by Hubert Saleur from, yes, there he is. Hubert, can you hear me?
Yes, I can. Can you hear me?
Yes.
So should I share my screen?
Please.
All right. Do you see it?
Yes.
Thank you.
Thanks.
Well, hello everybody. I'm sad I'm not there in person. It's been many years I do not come to Brazil conferences for a reason or another. I'm really sad about this. Hello Herman, I can see you. Hello Chico. Ciao Giuseppe and ciao everybody else that I cannot see. So it's of course an honor to be giving this talk. I must say over my whole career, I've regularly been amazed at Chico's papers. They're always relevant, always new, always exciting and easy to read also, which is a quality that is not so common when you think of it, and I'm really very thankful for his work over the years. So today I want to discuss a little bit an obsession of mine, which is the solution of the ON and in fact Q-state post-model conformal field theories in 2 dimensions. This is a very old problem which we were already working on back in the early 80s, and it keeps coming back as more and more technical progress is being realized. Lately it's been the bootstrap, and then more recently it's been these concepts of categorical symmetries and generalized symmetries that people in quantum information are excited about, among others. And here again, I think the ON model is playing an important role. So what I've prepared is a very simple talk, at least at the first part, and then we will see how far I've gone if I launch into the second part or not. I will, of course, define the ON model more precisely, but for now, let me say that this is a model we want to define for n, the quote-unquote number of components, being a complex number. And I will mostly discuss n real, but in fact, there's a lot to say about n complex also. And the way to define this model is by some sort of analytic continuation. Physically, if you want to think of this model, there are 2 equally relevant incarnations. One is the simplest. I think it's simply to think of the ON Landau-Ginzburg theory that we all know about. But imagine putting it in 2 dimensions. And imagine continuing n to n real or complex by one strategy or another. For instance, by doing diagrammatics or epsilon expansion, and then giving to n whatever value you want to give it. This is an interesting situation if n is real and smaller than 2, or if n were to be complex, in fact, real part of n is smaller than 2. In that case, in fact, the model, even though you're in 2 dimensions and have a continuous symmetry, does have a second-order phase transition. The reason why it does and why it escapes the Mermin-Wagner theorem is interesting, because the model is non-unitary. It's a point I will come back to again and again. When you do analytic continuations in n, usually you end up with signs in 3-point couplings, Clebsch-Gordons, norm squares, you name it. These signs indicate that your theory is not unitary, and if it's not unitary, the Mermin-Wagner theorem doesn't hold, and you can, in fact, have spontaneous symmetry breaking. In particular, therefore, you can have a second-order phase transition. Alternatively, it's also interesting to think of the ON model from the other side, so to speak. Look at the nonlinear sigma model, which, again, you can see flows to weak coupling for n smaller than 2, or in fact, real part of n smaller than 2. Once again indicating that the symmetry is spontaneously broken, while if n were greater than 2, the coefficient in the beta function would be positive and the symmetry would not be broken. So there is a low temperature phase described by the model, and this low temperature phase should admit a critical point. The question is, what is this critical point? And it's believed that it's in the same universality class as the Landau-Ginzburg model. So in a nutshell, what is interesting essentially is values of n which allow a bunch of new interesting physical properties and phenomena, in particular spontaneous symmetry breaking. Especially interesting is the limit n goes to 0, where of course we can have connection with descriptions of disordered systems, replica symmetry, replica limits of models like polymers, or in fact the integer quantum Hall effect transitions, and so on and so forth. So that is the model, and it's been really a puzzle for all this time, because there are a bunch of things we don't really understand when we try thinking about ON with n equals, say, square root of 2, or even worse, n equals some random complex number. What do we mean by symmetry if n is not an integer? what is the corresponding CFT? Surely it is not unitary, but what kind of CFT is it? Does it, for instance, have a discrete spectrum, a continuous spectrum? Is there a well-defined set of primaries that's close unto themselves under OPEs? What happens to the continuous symmetry? If we have a model with a continuous symmetry, are we having currents? What is the algebra of the currents? What are the consequences of non-unitarity? Is the theory logarithmic? How does this manifest itself in physical properties, and so on and so forth? These are all the questions that have been really bugging me, at least, and many people for many years. And I think we're starting to know the answer. In fact, I would say we know the answers to all these questions now. But the answers are technical, they're complicated. So today I'm only going to illustrate some points, and I'm mostly going to focus on symmetry. Now, it's probably time to define the model a little bit better. And in particular, I want to emphasize right away that this theory is not a Vesumino theory. The first natural way to think of such a model would have been to say, oh, well, I have an ON symmetry, so it's continuous symmetry. Probably I have currents, probably I have a Kac-Moody algebra. Let me look at some ON Vesumino CFT and let me continue in N, see what happens. Well, you can do this, but it has no relationship with the model we want to describe. In particular, say the model at n equals 1 should be the Ising model, and certainly there's no way to think of the Ising model as some sort of Vesumino theory. So the way everybody tackles this model is starting from the lattice. The reason we start from the lattice is because if we deal with a finite lattice, we do have analyticity in N, we can do continuations in N, and then we can take the continuum limit, and in particular, I should say the thermodynamic limit, and in particular, within the thermodynamic limit, the continuum limit. It's important to emphasize that if we were doing things the other way around, we might encounter some difficulties. If we took first the thermodynamic limit and then tried to analytically continue in N, we might encounter some surprises, at least in the low temperature phase, not the high temperature phase. So let's therefore take a lattice. The honeycomb lattice is the lattice of choice, following the old work of Bernard Nienhuis. And let's define on this lattice a model starting with vectors S with n components and the nearest neighbor interaction, Si.Sj. And let's moreover simplify the action so that instead of having an exponential beta Si.Sj, we simply take the first two terms in the expansion of the Hamiltonian and define the partition function on the lattice as the integral over all the spins of the product over all the neighbors of 1 plus k Si.Sj. This is our definition of the model for a finite lattice. And of course, this is a polynomial in N, which we can continue analytically in N to define what we're going to call the ON model for N complex. And by the way, we could do the same for POTS. There's a Q here. I'm not giving you the equivalent expression for POTS, but trust me, it's possible. Now, this model is beautiful for a variety of reasons. The most obvious is that this model admits a geometrical interpretation as a loop gas. If we expand the partition function in power of k, just like we would get in the diagrammatics for the 5-4 theory, we will get loops along which components of the vectors Si can propagate, resulting in a partition function which can be written as a sum over what is called a dilute loop gas. I have written an example of a configuration of the dilute loop gas here with 4 loops. These loops are very important, non-intersecting and self-avoiding. And we have a fugacity k per edge and n per loop. K is like the temperature. If we adjust the temperature to its critical value, which is well known exactly, the model is critical and has a second order phase transition. The continuum limit of this model is what I'm going to call the ON model CFT. And that's the problem I want to solve. This is a model that's called dilute because there's another version where K would become very large and the model would be kind of packed. It is what's called the dense version. It is a sort of low temperature phase of the ON model, but one has to be a little bit careful with this interpretation. I'll get back to this later. It is also a model that our colleague mathematicians love. It's called the conformal loop ensemble, and work on this model, as you know, via SLE and other questions, has led to, so far, 3 field medals, 2.5 French, I would say, and there's probably more to come. So this is definitely an exciting model. It's also related with the Isergin-Korepin spin chain, which is a spin chain based on spin 1, not unlike the models that Giuseppe was discussing earlier. Now, newcomers to this field always are suspicious about the model. It's very important to emphasize that it is a very robust universality class. The fixed point we obtain by perturbing a Gaussian model by repulsive interaction is extremely stable and really very unique. What I mean by this is we could define the model in more complicated ways without changing the universality class of the critical point. We could, for instance, instead of the expansion 1 plus k si dot sj, we could have the whole exponential. We could also, and this is what I will discuss a little more, allow crossings, like the ones I have drawn on this cartoon, which is the same model on the square lattice. It is well known, it is a fact that's been well established, that crossings are irrelevant and they don't matter in the continuum limit. We are definitely dealing with a very, like I say, robust universality class, and this is an important fact for what's going to come later. Okay, so some properties have been known in this model for 40 odd years, and I think Chico actually may have worked on this. I will mention some of his works later. What's been known has been the central charge and many of the critical exponents. So in the past, people focused only on n real. I will keep doing this, and it's well known in that case that the model has a critical line for n between -2 and 2, and if you parameterize n is 2 cosine pi over x, the central charge is 1 minus 6 over x plus 1. You go from c equals 1 when n is equal to 2. This is in fact the Kosterlitz starless point of the xy model in that case, to c equals -2 when n is equal to -2, and that's a theory of free charge or so-called symplectic fermions. For the SLE aficionados, the kappa value is 4x over x plus 1, or alternatively 4x plus 1 over x. Some exponents have been known for quite a while. I'll discuss them. And the point is that for many years, the correlation functions have not been known. In fact, the Dodsenko-Fatayev construction kind of indicated that they should be 0, which obviously is not true. And there's been a lot of progress in the last, I would say, 5 years, 10 years, due in particular to the bootstrap technique, and in particular also to progress in representation theory. So this is progress that's been done by a bunch of people. Of course, I am biased. I'm citing mostly myself and collaborators. But there's also been work by people in Italy, in particular Aldo Delfino and Jacopo Vitti, Marco Pico, Raul Santachiara, Gorbenko, Zan, and the group around Ryskov have done a lot of work on this. And then the group in Saclay and my former student Clef also. So here, so you see it's a huge problem. And what I want to discuss mostly are symmetry features. So in fact, there will be little bootstrap in what follows, and I will mostly discuss symmetries. And it's already very fascinating. So let me now jump ahead a little bit and discuss the torus partition function. It's very funny that the torus partition function for this model was known as early as 1992 by a work by Di Francesco, Zuber, and myself, and yet it was not understood. I would say the understanding is very recent, even though there was some progress we made with Nick Reed in 2007, but really what really is going on became understood quite recently. So what's about the partition function? Well, let me remind you that thanks to John's seminal work in '88, we know that the partition function on the torus is very useful because it encodes the operator content of the theory. It is, in a conformal language, the trace of Q to the L naught minus C over 24, Q bar to the L naught bar minus C over 24, and therefore, if tau is the torus parameter, right, this partition function should expand as a sum over all the fields in the theory, the primaries and their descendants, of Q to the H minus C over 24, Q bar to the H bar minus C over 24, times degeneracies. And these degeneracies are very interesting if you want to understand what the symmetry is, because the degeneracies typically give us the dimensions of the irreducible representations, right? In the case n integer in particular, we expect that these degeneracies are dimensions of irreducibles. So the identity H equals H bar equals 0 should come with degeneracy 1. The order parameter of the ON model at criticality should come in the vector representation. It should come with a multiplicity n, and so on and so forth. Well, degeneracies will exhibit some striking features. Now, before I move into these features, let me emphasize once again, the way this kind of calculation is done is by calculating with n integer, then continuing in n, and then taking the continuum limit. This is, again, something I think is important to emphasize. All right, so now let's move on details. Like I said, the exponents have been known for very long. And if we parameterize the central charge y minus x over xx plus 1, we're also going to parameterize the exponents by using a Katz-like formula, even though many fields are not degenerate, but we can always formally use this formula, where HRS is x plus 1 r minus xs squared minus 1 over x for xx plus 1, and RNS don't have to be integer. All right, so the partition function in fact expands on a bunch of fields. There are the fields where R and S in fact are integer. They come in this part here. And then there are the pieces where R in fact is half integer and S is a rational. In fact, many rationals. The only constraint is that R is integer or half integer, and the product SR is an integer. So if, say, R is 27, S can be any multiple of 1 over 27. That's a lot of rationals. As you will see later on, I will show a cartoon to illustrate the fact that pretty much the labels S are dense on the interval 0, 1, modulo a certain condition. So there's a lot of conformal weights. This we've known since the early 90s. A word has to be said about the fields. Some fields come with integer labels, R and S, and therefore you know that there is a state of vanishing norm square in the Verma module. The question is whether this state of vanishing norm square is 0 or not. In fact, for the fields here, it is indeed. So there are in the ON model fields which are exactly degenerate, which means there are fields which obey exactly the Virasoro degeneracy equation. A small set of fields, including the identity. There are many other fields whose labels are also integer. This would be the case R integer and S integer in this second term, which is allowed. These fields have null 0 norm square state, which are not degenerate, let me backtrack. They have 0 norm square states, which are non-zero. So these fields are fields of 0 norm square state. They are non-zero, which means the differential equation a la BPZ does not hold, which means the theory is logarithmic. This is something we didn't know at the time, but now we know it. So the 4-point functions of these fields are not solutions of BPZ. That's something else. And then there are all the fields where R and S are rational, non-integer. For these, there's no BPZ hope, no degeneracy equation. The bootstrap is necessary. Okay? I'm not going to discuss the bootstrap much. However, what I want to discuss is the degeneracies. So all the fields on the left come with degeneracy 1. They are, if you wish, all in the identity sector. All the other fields come with fancy degeneracies, which are right in the form ERS plus delta R1 delta S into Z plus 1. What is this ERS? This ERS is a very bizarre thing, which we calculated with Nick Reed almost 20 years ago. It has the following form. You give yourself labels RS, and you have a arithmetic object where you sum for R prime equals 0 to 2R minus 1 of some exponential times this X. Now, X is of the form Q to the D plus Q to the minus D. So here I must take Q to the 2R vector R prime, wedge R prime, and the complex conjugate. Q is related with N. And finally, wedge means, and that's the arithmetic aspect, greatest common divisor. So for each R and R prime, you need to find the greatest common divisor of 2R and R prime and build this bizarre object XD of N. It is very interesting, but I'm not going to explain really where it comes from. Rather, I just want to give you examples. The point is that in the end, it's just a way to write polynomials in N. And these are the first examples of polynomials in N that we obtain. Remember, R is a half integer, S is a rational. So here are the examples. R is 1/2, 1, 3/2, 2, and so on. For each value of R, you take S rational so that Rs is an integer. And here are the first few polynomials. N, you observe, is the vector representation. N minus 1 over 2, you all know, is the adjoint of On. The others, if you know your On representation theory a little bit, you may observe, are not dimensions of On irreducibles. What is going on? Well, what is going on is that the degeneracies corresponds to groupings of On representations. So all the numbers I have on this table are associated with spaces of multiplicities are called lambda Rs. And the point is these lambda Rs, once again, are not irreducibles of On. They're gluings of irreducibles of On. Or I don't like to use the word gluing because gluing suggests there are extra algebra generators. I'm not sure what's going on here, but they are groupings. So to put it in simple words, you take several On representations and you group them together, and this gives you the multiplicity of the conformal fields. The groupings grow extremely fast. Here you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 representations are put together to make one multiplicity space for the field with R equals 5/2 and S is 2/5. The larger the R, the larger the grouping. In fact, there's a beautiful mathematics here that I'm not going to describe, but because I want simply to explain where this is coming from. But definitely these degeneracies they're very large and they're compatible with On. We are not saying, oh, away from n integer, On doesn't make sense. No, what we're saying is that away from n integer, it's kind of hard to keep the whole On. What you keep is some sort of larger algebra than On in a sense, but it has a slightly different nature. I will try to explain this. Important fact is that the symmetry is global. It's not left factorized. This is something you can deduce easily from the multiplicities of the fields with conformal weight 1, for instance, or more generally the fact that none of these multiplicities are products. So it's not a Weis-Zumino model. Other important point is that the degeneracies will be the same for the model away from criticality. If I took K different from Kc, we would still have these degeneracies. And if we took n integer greater than 2, the model would not be critical, but it would still have these degeneracies, the loop model. All right, so what's going on? And to understand what's going on, it's interesting to understand physically the nature of the fields, which are so far extremely abstract, not very physical. So the first type of fields we're having, the most important type of field we're having are the so-called watermelon operators. This label R in the partition function here, R is a half integer. R corresponds to the number of legs in the loop representation. So in particular, R0 are the operators that create two R legs. That's why R is a half integer, because the number of legs can be odd or even. R is 1/2, for instance, is just one leg, the vector representation. So Orville fields are in the theory. And then the phi RS, the other fields here associated with this character, they're just obtained essentially by decorating these basic watermelon operators by phases. It's not very complicated. Now, if you are dealing with a theory that has only ON symmetry, you would expect that every field should be associated with an irreducible representation of ON, that there should be a one-to-one correspondence between representations of ON and primary fields. But think for a minute, the fact that we're having a non-crossing condition in our model has tremendous consequences. It has the consequence that, in fact, not every Young diagram of ON can give rise to a different primary field. This is because in order to realize all the ON tensors, and I will explain this more later, but I want to give you a first hint right now, in order to describe the ON tensors, you would need sometimes to allow for line crossings. But if line crossings are not allowed, different tensors should behave the same. For instance, in ON, the difference between a fully symmetric and a fully anti-symmetric tensor is the way you describe nearest neighbor permutations. In one case, you give a plus sign. In the other case, you give a minus sign. But permutations are sometimes associated with crossings and sometimes not on the plane. If the ones associated with crossings are not allowed, you will not see the difference between a plus sign or a minus sign. This means that there are some fields, like for instance the field with R equals 3/2, we should come with a multiplicity that groups the fully symmetric and the fully anti-symmetric representation. This is what you see here, where the 3/2 field mixes indeed, the fully symmetric and the fully anti-symmetric. So the non-crossing condition is what should explain the multiplicities. But it's very hard to go from the non-crossing idea to the multiplicity idea. And that's what I want to explain in the rest of the talk. Now, at this point, you may say, oh, but we argued that the crossings didn't matter, and that if we allowed crossings, we would get the same universality class. Well, yes, that's true. So if we had a model with crossings on the lattice, the eigenvalues associated with the field corresponding to the fully symmetric and corresponding to the fully anti-symmetric representation would be slightly different. But in the scaling limit, they would coincide. So the good statement is that the scaling limit, that is the ON CFT, has more symmetry than ON. And there is no CFT with only ON symmetry, as far as we know. It seems like it's not a Vesumino, but it still has more symmetry than ON. It is this bizarre theory that corresponds to non-crossings of the lines. All right. Now, the non-crossing is a pedestrian way to say something that is very meaningful algebraically, and it has something to do with Chauvel duality, and it is in fact what can be used very conveniently to describe the meaning of ON away from an integer. So imagine you act on the tensor product of ON representations for an integer. You're going to have ON acting on your Hilbert space, and there is what's called a Chauvel duality between ON and the set of observables that commute with ON, what's called the centralizer of ON. And in the case, and this set of observables itself is an algebra that depends on the representation you tensorize. In the case of the vector representation, it is the Brouwer algebra. Brouwer algebra is a famous algebra in mathematics, and this algebra admits a diagrammatic representation. No surprise. The diagrams that physicists draw in their high temperature expansions are nothing but the diagrams that mathematicians draw in their recoupling theory, from Brouwer, Penrose, all the way down to Tsvetanovic's book, for instance, on recoupling theory and group theory, and so on and so forth. So the Brouwer algebra is an algebra that involves loops, because it's an ON model, but the loops cross. That's the point of the Brouwer algebra. The loops cross, and in fact, aside, the good way to define ON as a symmetry for n non-integer is really a categorical way based on not so much ON, but its centralizer. It's really based on the Brouwer algebra. It's called the Brouwer category. Here we are not allowing crossing. So what's happening is we're having an algebra with loops where the loops are not allowed to cross. You all know this in this room. This is the Temple-Ellib algebra. So the mathematics hidden behind the grouping of ON representations is a very interesting mathematics, which I'm not going to discuss. I didn't want to give a very long talk, but it's the mathematics of branching rules from Brouwer algebra down to the Temple-Ellib algebra. And this mathematics had not been done, and this is something we did in 2022. We in fact proved the branching rules from Brouwer down to Temple-Ellib, in fact, periodic Temple-Ellib. And this is what allowed us, by the way, to obtain a analytic expression for these lambdas. Very complicated one, but now we have an expression. Sorry. All right. So I'm not running out of time so much, but anyway, I don't want to give a very long talk. Let me now go a little bit further. Now, okay, this model doesn't allow crossings. Very nice. Or if you allow crossings, anyway, they disappear in the continuum limit. Good. Okay. So because there are no crossings, the Chauvel duality between ON and Brouwer is changed. It is a Chauvel duality between Temple-Ellib, periodic Temple-Ellib, and something else, something that extends ON. What is it that extends ON? Well, we've looked for a long time trying to find extra generators that would glue the representations of ON together and define some sort of, I don't know, Hopf algebra of some sort of other. We have not been able to find it, and so we still don't really know what the answer is. But I have a hunch that the answer is something else, that the answer has something to do with topological symmetry. So let me say, in very simple terms, what topological symmetry might be. What does it mean, topological symmetry? Well, let's take the ON model, the one I have here on my lattice discretization. I'm not very pedagogical. I should have drawn the loops in blue instead of red. Imagine the loops are blue, just for a minute. And then let's imagine that on top of my diagram, I draw an extra loop. And that loop doesn't really live in the plane. It lives above, right? So this is what I represent here. The loop lives above. Now, of course, what I mean by this is that I allow myself a Reidemeister move. I allow myself to move the loop away, okay? I want to think of this loop as a topological defect. In fact, a topological defect line in a Euclidean version. It becomes a real topological defect in the Hamiltonian version. This is a topological defect line. But what does it mean to add a loop on top? It doesn't mean much. Well, yes, it does, because we have a solution of the Yang-Baxter equation at infinite spectral parameters. So what I mean is that, in fact, this loop, it's not so much on top. It really belongs to the other loops. It really belongs to the plane. And whenever I have a red loop, the topological loop, crossing an ON loop, what I mean is that I have a new type of vertex in the model. A new type of vertex, which I can decompose, like what's happening on the right-hand side here, minus q to the 1/2, and remember n is q plus q inverse, times this diagram, plus minus q to the minus 1/2 times this diagram. So my red loop, in fact, gives rise to new configurations in the ON model. New configurations with no crossings, just like before. I changed the weights of some configurations. And the point is that it is a topological defect. I know it because this is the result of just having a loop on top, which I can move around by a Reidemeister move. So of course it doesn't affect the partition function. It is a topological defect, but it is a non-trivial object. It's a topological defect, like every topological defect, that's going to multiply the partition function by the expectation value of the topological defect in the ground state. That's n, the weight of the loop. and modify correlation functions and so on and so forth. But on the other hand, it commutes with the Hamiltonian. It is a symmetry. So this defect I can also define in the Hamiltonian version. It gives me an operator that commutes with the Hamiltonian. So I have an extra operator that commutes with the Hamiltonian, which is not an ON operator. It is also commuting with one. It is something else. And I think that is what explains the grouping of the representations. And here is to illustrate the fact that the defect does modify things. So for instance, if you have a line, correlation two-point function of an order operator going from one point to another, and then you insert a topological defect line around the insertion, well, you modify the object. You modify it by, in fact, you multiply it by this factor. All right, so this topological defect is an operator. It commutes with the Hamiltonian of the model with non-crossings, but that's the key point. It does not commute with the Hamiltonian with crossings. So the topological symmetry, the fact that there's D that commutes with the Hamiltonian, is a symmetry that prevents crossings. It's very important. It prevents crossings, and therefore there are two kinds of physics in this model. There's the physics that preserve the topological symmetry, and there's the physics that does not preserve the topological symmetry. In one case, you don't allow crossings. In other cases, you allow crossings. In other words, what we are learning is that in the ON model, if, say, we change K, if we move away from the critical point, K different from Kc, still not allowing crossings, we preserve the topological symmetry, and therefore we have a certain physics. If, on the other hand, we were to modify K and at the same time allow crossing, we would presumably have a different physics. And in fact, it's well known because the model with crossings and K larger than Kc was also studied some years ago. And it's a model in a different universality class from the dense ON model. So what's happening in the ON model is something that was not quite understood so far. The pure thermal operator corresponding to K not equal to Kc has a flow to the dense phase, the well-known dense ON model of Nienhuis, but the and this flow is preserved by topological symmetry. And the minute we allow four-leg crossings, we break the topological symmetry and we flow to another fixed point. In fact, that other fixed point is the fixed point has been called the sigma model. It is, in fact, really the genuine low temperature phase of the ON model, ON over ON minus 1. It is a Goldstone phase with logarithmic correlations, vanishing critical exponents, and so on, very different from the ON dense phase. So the symmetry for this physics is absolutely crucial. Now, of course, the symmetry would also be crucial for the bootstrap because symmetries was determined four-point functions. So I had a huge number of slides on the bootstrap, none of which I'm going to go over because I think it's late. Only thing I want to describe briefly is the values of R and S. When I describe the partition function of the model, I said, oh, it's kind of dense, these labels, and I'll show you a cartoon. Where is the cartoon? Here's the cartoon giving you the values of R and S for the model. You see that R is half integer, and for a given R, here are the values of S. You see as R increases, S gets more and more dense on the axis. And in fact, the values of S are dense. So it's not a theory with dense exponents, they're not, but it's a theory with dense values of the CATS labels. This is important in the OPEs, so I'm not telling you anything about the bootstrap, it's too long, but important fact, all these fields appear in the OPEs. So for instance, the OPE of the order operator with itself in the ON model couples to all the fields in a theory. All these guys in the diagrams, except for a small parity constraint, they all appear in the OPE of the order operator. Particularly important is the fact the number of legs is not a conserved quantity. Now, this is again very important, and the OPEs constrained by ON symmetry would have a very different look from the OPEs that are not constrained by the ON symmetry, but constrained by ON plus this topological symmetry. So one of the remarkable facts we saw when we solved the bootstrap is that the bootstrap knows about the fact that the loops are non-crossing. You may think that if you did the bootstrap with this spectrum, maybe you would find as many solutions as there are ON invariants. No, there are fewer invariants because the symmetry is larger, and the bootstrap knows about this. So all this blah blah about topological symmetry and loops, crossings, and non-crossing, in fact, it would come out of the bootstrap by a miracle. We don't really understand. Anyway, I think this is it for today. Let me go to a conclusion. I only wanted to discuss symmetries. That's kind of what I did. So it's important to realize that even if n is not integer, Amy-Noether's theorem still holds. There are still counts with weight 1, 0, and 0, 1. I didn't say much about them, but they're there. They're in the adjoint. They're non-chiral, which means they have conformal weight 1, 0, but they are 4-point functions, and OPEs depend both on Z and Z bar. That's why the model is not a Vesumido model. I don't think the grouping of ON representation follows from an algebraic extension of ON. I think it's something else. I think it has to do with topological symmetry, although I'm not totally sure how to put this into equations yet. Other than this, well, it's humbling to think that we are still working on refinements of the major works of the early 80s. Among all of Chico's work, I would say the one that has most influenced me is this, and my students, because it's one of their mandatory readings when they come in the group. It's this amazing paper he wrote with Murray and Michael Barber in '88, Conformal Invariance, the X-axis spin chain, and the operator content of two-dimensional critical systems. Like I said, we're just refining this work. 45 years after the fact, it is humbling. So thank you, Chico, and happy birthday. And here is a politically very incorrect Brazilian slide to wish you a happy birthday. Thank you.
Thanks a lot, Hubert. Chico is very happy with you. This is last slide. Me too.
Stop share. There we go.
Questions, comments?
Oh, well.
Hubert, first of all, thank you for you to give us this profound lecture that pick up all the old stuff and really came in to answer a deep question, to try to understand this ON really in the middle when you don't have an integer, whatever, how to look at those models. And it's quite interesting that it's just not Vesumido. You have, you know, this crossing, non-crossing, protected somehow because of this topological new symmetry that appear up. That's quite beautiful. Okay, thank you very much for your kind presentation. Thank you.
Thank you, Chico. Bye-bye.
Bye-bye.
Oh, I don't see any more comments. Hubert, thanks a lot. Thanks for...
Okay, no problem. Thank you very much.
Hope to see you soon in person.
Bye-bye.
We go for a short break downstairs, and we resume with Fabian Esler in 15 minutes.
Deixa eu perguntar uma coisa, o André Malvese, ele quer vir amanhã?
Esler. So it's time to resume with Fabian Esler from Oxford. Esler, can you hear me? I'm not hearing you.
Make it bigger.
Can you see it now?
Yes.
Yeah, always fine now.
Yes, yes, it's fine.
Okay, great.
Okay, Fabian, it's you.
So take it away. Well, thank you very much. First of all, I'd like to thank Jose for putting together this workshop on this great occasion. And I'm very, very sad I'm not able to be there in person, but you know, some of us have to teach. So now I'll be talking about some work I have been doing for the last year or so with Werner Kraut at the ANS, and here's a picture of Werner. And it's about, as you will see, a Bethe-Ansatz-like solution for some kind of interesting kind of stochastic process. So let me put this in a little bit of context. So now, first time I met Chico was in 1994. So this is roughly what he looked like. And at the time I was a postdoc of Vladimir Rittenberg's. And this was just after they had published their very influential work on reaction diffusion processes. And out of all of Chico's work, so I've learned quite a lot from Chico over the years, of course, and the paper Hubert mentioned, of course, I also studied very carefully. There were many other works I used over the years, but the most influential one arguably was this one, where they pointed out that a very large class of stochastic processes, mostly reaction diffusion problems, could be viewed and could be analyzed in the language of non-Hermitian quantum spin chains. And so this I learned when I was with Vladimir in the early 1990s from this paper, and this has been with me ever since. And the story I'm going to tell you about today is about a model that can be viewed in this way as well. But so the background of our work is very different. So the background is basically numerical methods in statistical physics, in particular Monte Carlo algorithms, or more precisely Markov chain Monte Carlo algorithms. So there's of course a huge community and a huge literature on that subject, and Werner Kraut is one of the world experts. So what a problem of interest in that area typically is to find the equilibrium distribution of an interacting many particle system, such as hard spheres in d dimensions. And so these are computationally extremely hard problems. And the method of choice in a lot of these problems are Monte Carlo simulations. And as all of you know, so a Monte Carlo algorithm I can think of in terms of a Markov chain. So I have a probability distribution of configurations of my system at a certain time step, which I call t-1. And then I have a mechanism, a set of update rules, which I can encode in a transition matrix that tells me how to arrive from this probability distribution at time step t-1 at an updated probability distribution for the configurations of my system at the next time step. And so typically in these problems, what people are interested in is the late time limit in which the algorithm hopefully converges to the steady state, for example, to the equilibrium state that is of interest. And so one of the things that one aims to do in this business is, for example, to minimize the mixing time, so to minimize the number of steps required to reach the steady state to a given accuracy. And there are lots of, as I said, there's a huge literature, and there are lots of very, very clever algorithms that do this. Now, one way of improving these Monte Carlo algorithms are so-called liftings, so lifted Markov chain Monte Carlo algorithms. So some of the seminal papers in this method are listed here. And again, Werner has contributed quite a lot to this subject. And they are based on the following idea. So whenever I have a Monte Carlo algorithm, I have a configuration of my hard spheres, let's say in my d-dimensional space or d+1 dimensional space. D-dimensional space. And then I have a set of rules that update this configuration for me. And lifting basically means you introduce a very clever enlargement of the space of configurations that you update in time. And then, so you work in a larger space, yeah, and do your simulation there. And in the end, you project back down to, let's say, the physical degrees of freedom. And by doing this, you can achieve very dramatic speedups. And so let me explain this in a very simple example. And the example I've chosen here is a well-known stochastic process, the totally asymmetric simple exclusion process. In one dimension. So what that is about is it basically describes the driven motion of hardcore particles on a one-dimensional lattice, either on a ring or with open boundary conditions. So these particles are hardcore particles, so each side can either be empty or occupied by one of these hardcore particles. And then the Markov process that one considers is one randomly picks a particle and tries moving it to the right. And if the neighboring side is empty, so for example, so this is a given configuration, so I pick this side here. Now the neighboring side is empty, and if it's empty, I just move my particle to the right with a certain probability, with a certain rate. And if the side to the right of the particle is already occupied by another particle, I cannot move. So this move gets blocked. Yeah. So and this describes this stochastic process, a totally asymmetric simple exclusion process. That has attracted a lot of attention over the last, I don't know, 25 years or so, because it's a lattice version of the KPZ equation. And with regards to, so if I now start in some initial configuration and update it following these rules, I converge to a steady state, and the steady state is very simple in terms of the TARZEP. It's a completely mixed state, but a state that carries a current. And the mixing time, so to speak, in this case would be L to the 5/2, where L would be the size of the system. And as many of you will know, one can consider this also with non-trivial boundary conditions, and then the story becomes much, much richer because there are boundary-induced phase transitions, etc., etc. Okay, so this was just a very brief review of this TARZEP. Now, one can consider a lifted version of that stochastic process as follows. So one enlarges the configuration space. So the configuration space of the TARZEP itself is basically a tensor product of two-state systems, because on each side I can either have a particle or no particle. Yeah, and a configuration then would be a certain sequence of particles on a given set of sites. And now we enlarge this configuration space by introducing a new variable, which we call a pointer particle. So that's a different kind of particle. But I only introduce one of these, yeah, and all the other particles are kind of like ordinary regular particles. Okay, so here I have a configuration of my particles on my one-dimensional chain. So now this one here, I call now the pointer particle. Okay, so that's my configuration at step T. And now I update my configuration by simply moving the pointer particle to the right if the neighboring site is empty, or by moving the pointer to the next particle if the site is occupied. So that's a completely deterministic process. So in order to obtain a lifting, one introduces stochasticity by running this deterministic process for a while and then stochastically changing the pointer particle. Now, the steady state of this stochastic process that's obtained in this way is the same as for the TARZEP, but the mixing time is a lot faster. So we basically get to the desired state much more quickly. So L squared instead of L to the 5 halves. Okay. So now, what we have done now is to consider a different lifting of this totally asymmetric simple exclusion process, which is described here. So the drawback on with regards to the lifting on the previous slide was it's basically a deterministic process, and then by resampling, stochasticity is introduced, and so this is undesirable. So what we do instead is we define a stochastic process in the following way. So we have a configuration of particles on our one-dimensional chain. So these are the particles, and there are lots of vacancies. And one of these particles is different from the others, so that's my pointer particle. And now I update the system. So my time step is defined as follows. With a probability, or with a rate 1 minus alpha, I hop this particle with a pointer to the right. So I hop from here to here. So I end up in this configuration. This would be a right hop. But with a rate alpha, what I do is I hop this particle to the right. So I would, that's the move I had here. But then I move the pointer from the particle it's at to the previous particle. Okay, so I move the pointer which was here over there. And I do this with rate alpha. So importantly, and I stress this, this move in general is non-local in space, right? Because here it's a few sites, but it could be, I don't know, 100 sites, 1,000 sites, whatever. So that's a non-local move. And it's that non-locality in a sense which can improve how fast you get to the steady state. So I've discussed the situation where the site to the right of the pointer particle is empty. If it's occupied, I do exactly the same thing. Yeah. So with rate 1 minus alpha, I move now, because the site is occupied, the pointer, but then with rate alpha, I move the pointer back to the previous particle. Yeah. And so those are the complete update rules of this stochastic process. So we call this informally the STARZEP. So where S stands for super, yeah, because it mixes very fast. And this can be viewed as a discrete version of a Monte Carlo process that was studied previously by Van der Kraut and collaborators. So some one-dimensional hard sphere factor field Markov chain Monte Carlo. So in case any experts in that area are in the audience. Okay, so what we now want to do is we want to basically study this stochastic process. And it turns out very surprisingly that this stochastic process can be solved by something which is very similar to a Bethe-Ansatz. So I call this a Bethe-like ansatz. And in order to see this, we now proceed basically following this very, very beautiful work. Yeah, and oops, now, okay, so we write the stochastic process I have described on the previous slide as a three-state model. So either my side J is empty, so that's configuration 0, or it's occupied by a particle that I call configuration 1, or the pointer particle is at side J, that would be configuration 2. And then, so altogether I will have 3 to the L configurations, which I can label in this way. On each side, 3 possible configuration, L sides. And the associated probabilities I call P, the probability, which is a function of all these configurations. Okay, and equivalently, I can label these probability distribution functions in a somewhat different way. So I introduce a set of coordinates which are the positions of the particles. And the particles are either regular ordinary particles or the pointer particle. Yeah, so this tells me all the positions on my ring or my chain where the particles are. And then this sequence of label sigma 1, sigma 2 up to sigma L tells me whether the particle that's at position J1 is the pointer particle, so it has index 2, or is an ordinary particle. Yeah, so an example is written here. So the configuration 0, 0, 0, 1, 0, 2 corresponds to having an ordinary particle at side 4 and the pointer particle at side 6. And in the other notations, I can rewrite it as I have done here as P1246. So I have a particle at side 4, a particle at side 6. The first particle is ordinary. The second particle is a pointer. Okay. So that's the notation. Okay, oops. Now what we do, as I just said, we follow Alcaraz et al. And turn these probabilities into states, kets, by taking these probabilities, multiplying them by state vectors, yeah, which basically tells me what configuration I have on the jth side. So this state would be the state where I have no particles anywhere. And this is a product of Hubbard operators, which basically tells me, which turns a vacancy either into a vacancy or an ordinary particle or a pointer particle. So these are just ordinary Hubbard operators. So this gives me then basis vectors, which tells me what particle I have where. And then I just sum over all possible positions of these particles and all possible positions of the pointer. Yeah, so this would be now a general, this would be a general ket in some linear vector space, which encodes this probability distribution I had defined on the previous slide. And then the stochastic process, this star-ZEP or lifted R-ZEP, that is described by a master equation, which in this formalism here turns into an imaginary time Schrödinger equation. So I can write this as the time derivative of the probability distribution. I can write as a quote-unquote Hamiltonian times the probability distribution. And this Hamiltonian I can write in this form here in terms of these Hubbard operators. So these terms basically tell you I have a pointer particle hopping between two neighboring sites when the side to the right is empty. So this would be a hopping process of the pointer if I have two neighboring sites which are both occupied. And then I have this prefactor here, which is very important. So I have these rates I had noted before, but then I also have an operator here, which describes this non-local move of the pointer, so that permutes the pointer particle with the closest regular particle to its left. So this describes some complicated non-local interaction. So it's non-local in space. Okay, now the eigenvalue equation for this transition matrix or Hamiltonian I can write in this way. And the surprise now is this eigenvalue equation can be solved by a Bethe-like ansatz. So I can write for these probabilities an ansatz which looks a little bit like a nested Bethe ansatz. So I have a bunch of amplitudes, yeah, which depend on permutations, a set of all permutations of my n particles. And then here I have a product of, well, if you wish, generalized plane waves, where Z1, Z2 up to Zn are some complex numbers, and J1, J2 up to Jn are the positions of the particles. Yeah. So this is a superposition of generalized plane waves, and in that sense, it's like a Bethe ansatz, and it's nested in the sense that the ordering of the particles plays an important role. And then what one can show is substituting this ansatz back into the eigenvalue equation, one obtains a number of relations between these amplitudes, which for ordinary nested Bethe ansatz would just have a simple interpretation in terms of scatterings, two particle scatterings. And then these spectroparameters, they fulfill some complicated condensation conditions or Bethe ansatz equations, and the same holds here. So one can derive, we have derived a set of connection equations for these coefficients. They look a little bit strange compared to the usual connection equations, which involve just some two-particle S matrix, but there is a set of such equations. But they're a little bit unusual. Now, what's more unusual is these spectroparameters fulfill Bethe-like equations. So I'm considering the system on a ring now. So it's a set of n coupled algebraic equations for these complex numbers, Z1 to Zn. So here they are. And then I have one more equation, which involves also the eigenvalue, so the energy or the pseudo-energy eigenvalue here. Yeah. And so this is very different from usual Bethe ansatz-like problems where the energy enters. So here the energy enters the condensation conditions like a spectroparameter, so like a nesting in actual fact. Whereas in usual Bethe ansatz solvable problems, the energy would just be given in terms of these ZBs. And in the ordinary TARSEP, for example, this, which is also integrable, I should have said, this is the case. Yeah, so this is unusual, okay? But it has the same status as a Bethe ansatz solution of this problem, right? Because we have condensation conditions that give me the spectroparameters, and once I have the spectroparameters, I have the states, so the probabilities. Okay, so then we can analyze these as always. So we can first ask, well, what about the steady state? Well, the steady state by definition has E equals 1, and I can obtain it from these Bethe ansatz-like equations by just taking the limit where all these spectroparameters go to 1, and the corresponding probability or wave function describes a completely mixed state, so an equal amplitude superposition of all allowed configurations. And that is the same as the TARSEP, and which is good because from a good lifting, so this kind of procedure I've introduced, that is what one desires, what one expects. Okay, so that's the steady state. And then the next thing we have studied now is the excitation gap. So now if I look now at the logarithm of the eigenvalue, the real part of the logarithm is negative because I'm looking at a stochastic process. And the steady state, for the steady state, I have log E equal to 0. and all other eigenvalues have negative real parts, and the excitation gap refers to the eigenvalue, or to the state which has the largest real part of the log of the eigenvalue. And that describes how quickly at late times I approach the stationary state. So I call that the excitation gap. So that's also standard terminology in that area. Okay, so we can work this out. So in order to do this, we slightly change parametrization of these Bethe-Ansatz-like equations. But then one can find the solutions of these very complicated coupled algebraic equations that give me this eigenvalue with the largest real part. And so here I show some results for L over 2 particles on a ring with L sides. And the results are obtained by numerically solving these things up to 500 sides for now. And just for the experts in the audience, this is actually rather difficult. Yeah. So now the structure of the gap and also the distribution of the spectral parameters depends very much on this parameter alpha, which was a parameter of my model. And so first I consider alpha equals 0.4. So here I plot the distribution of roots. Here's the imaginary part of the roots. Here's the real part of the roots. And you see the roots approach as L becomes larger and larger and larger, some nice contour. Yeah. But there are some special roots, these ones here, and the different color codings for different system sizes, I should say. So there are some special roots which do something else, and you can think of these in some sense as analogs of boundary bound states as you have them in Bethe-Ansatz solver models with open boundary conditions. So why this is, if you want to know, you can ask me later. So that's the distribution of the roots. Then we can look at the scaling of the real and imaginary part of log E of the corresponding eigenvalue. And what we find is the real part scales like L to the -3/2. Yeah, so beautiful scaling here. Whereas the imaginary part scales like 1 over L. Yeah, so the gap collapses to 0 in the thermodynamic limit, but with some critical exponent. Yeah, which is -3/2 for alpha 0.4. Now, if we then go to alpha 0.5, you can have the analogous information. So you have some distribution of roots. The real part now scales like 1 over L squared. The imaginary part scales again like 1 over L. So this critical exponent has changed. And if you do it for alpha 0.9, the eigenvalue turns out to be real, so you get a distribution of roots which is invariant under complex conjugation. You can think of this as a bunch of deformed 2 strings for the cognoscenti. But now what we find is that the gap scales like 1 over L to the 5/2. So there's quite a rich phenomenology of the scalings of these excitation gaps. I should say that what I defined before as the mixing time is not exactly the same as this gap scaling. So the mixing time is basically the number of steps that you need to get from a worst case initial condition to a given vicinity of the stationary state. And so that we are not able at the moment to determine from the exact solution, but one of course can determine it numerically. So now that's all I can tell you so far. So this is how far we have gotten basically with this exact solution. So what we have done is we have introduced a lifted version of this very well-known stochastic process, the totally asymmetric simple exclusion process. And this lifted version is a new, an exactly solvable paradigm for a non-reversible lifted Markov chain. So we are quite excited about this. What we know, I haven't really talked about this, it gives you huge speed ups in mixing times for some of the regimes in alpha. From the point of view of integrability, it's very interesting, first of all, that it's integrable because this Hamiltonian, so to speak, is manifestly non-local. Yeah. It has local moves, so Hamiltonian has local parts, but then also non-local ones. But nevertheless, it's solved by coordinate beta ansatz. The integrable structure, in all fairness, so we don't really understand this at the moment. So in particular, I'd really like to know as well, what is the R matrix? So the problem is, this is supposedly the limit of a more general integrable class of processes, and we would need to know that in order to be able to talk about R matrices. So there's a little bit similar to the ordinary task set. I've shown you some results on the large system size scaling of the spectrum of the transition matrix, and it's very, very rich. Yeah, because the gap scaling depends very much where you are, and you have a bunch of different critical exponents. And these eigenvalues are typically complex, and the imaginary parts collapse much more slowly than the real parts in all cases. So that's what we have. There are lots of work remains to be done. So as I said, we would like to calculate mixing time, autocorrelation time, also from the exact solution if we can. We would like to generalize this to a lifting of the partially asymmetric simple exclusion process. Then, of course, one can ask, well, what happens if I introduce open boundaries, non-diagonal boundaries, where I input and extract particles? And perhaps the most important question is, well, the fact that this process now is integrable, does this tell us anything? Can it help us to understand detailed mechanisms understand the detailed mechanism for the speed up in the mixing due to the lifting? And with that, I come to the end of my talk. Happy birthday, Chico. I hope you liked the topic of the talk and the fact that it covers one of the areas you have contributed to greatly over the last several decades. So happy birthday.
Thank you, Fabian. Questions, comments? Yeah.
Hello, Fabian. You hear me?
Hello.
Hello. Chico.
Yeah. Chico, where are you? I can't see you.
Yeah, you can see?
No.
Okay.
But
maybe not.
So because I have to wait, I have to stop sharing. Now I can see you. Hey, yeah.
Oh, Fabian. Fabian, let me ask you something. But eventually, what you have a certain state, okay, which is, is just this white noise with conservation of particles, right? And actually, you would like to find just evolution operator, which we may call Hamiltonians. And so actually, you could go in a large space of all the possible Hamiltonians, who has as the leading state the same ground state, and try to see each one you go faster to that. So the idea one is to find a gapped one, not a massless one, right? So you found some massless guys who goes to the same ground state. But perhaps
yes,
you may find a massive one, so then you go faster.
Yeah, okay, I hear you. I mean? Yes, so this is something for you to work out.
Yeah. No, but actually in this paper you mentioned the end, there is something that in this direction for the, of course, it's a simple problem. I mean, a Potts model in one dimension, whatever, how to do a simulation go faster. There is some comments there. If you look, if you remember that. Now, the other point is the following one. When you enlarge your space, it's not clear for me. You do it in the sector of one only pointer, or you do all the arbitrary number of pointers?
No. There's only one pointer particle, right? I mean, so the lifting is quite simple. Yeah. So you basically have n-1 ordinary particles and one pointer. And the pointer kind of does these non-local moves and helps to mix very, very quickly.
But if I count also the empty places and put in a spin, this jump in non-local actually, but I have to consider, of course, not just one, but I can consider bigger spin. Then they are neighbors, this jumping, right? Like the mapping for the zero range process.
Yes.
If I do the zero range process, okay, I don't know if you remember that, then I transform this problem actually in nearest neighbors jumping. But then, you can have in a site several particles on the top of each other.
Yes.
And then it's not possible to do like that, to try to see that?
So, as I said, I mean, so there is a lot more we don't understand here that what we understand. I mean, so you see that there is a lot of literature on these liftings, and they come from hard spheres in d dimensions. And so we basically entered this topic with that background, and so we have now this one example, which is a simple one, which is inspired what they had before, and the surprise in a sense is, well, that model curiously is integrable, which you wouldn't expect. So I certainly didn't expect it. Yeah. And now the question, of course, is, well, can one generalize it further? Can you have further gains, etc., etc.? But so I don't know. I don't know the question. I don't know the answer to any of these questions at the moment. So at the moment, so I'm happy I was able to understand something. But yeah, so one certainly would like to push this much further. So it's a new. For me, it's a new area for Bediansatz to some extent. Yeah, because it allows you in principle now to prove things about algorithms.
Okay. I hope you find a solution before you turn 70.
Thank
questions, you. More questions? Maybe a simple one. You find that exponents 5/2 of in your finite size gap. This means that this is a different universality class from the not lifted the usual TASEP.
Yeah. Okay. So right? One has to be a little bit. Okay. So we have this discussion all the time. Yeah. So if you just take it as a stochastic process, and close your eyes, so to speak, and just ask what is the gap scaling, then in the ordinary TASEP, you would have 1/L to the 3/2. And if you look at the partially asymmetric exclusion process, you can have 1/L to the 3/2 or 1/L squared. And from the point of view, just as a stochastic process, so here we clearly have something different. So because we have 1/L to the 3/2, 1/L squared, but also 1/L to the 5/2.
And the culprit is the non-local interaction. That's what you're saying.
Yeah, exactly, exactly. But so if you now look at other quantities like this mixing times, etc. So as I said, they are not related in a completely straightforward fashion to the gap scaling, but you can ask analogous questions, and they're a little bit more difficult to answer.
Okay.
But as a stochastic process, a priori, it's a very different stochastic process to the TARSEP. All we know is the steady state is the same, yeah. But in general, you approach it in a different fashion.
Thank you.
Hi,
Are there other questions, Angela?
When
go
ahead. So nice talk, very clear. But I have a question. When you mentioned huge speed up in mixing for some value of alpha, do you have some value, some number in mind? What do you mean by huge? Specific
yeah,
number?
so you see, so what I said is, okay, now, so for the order, so if I look at this mixing time, so for the TARSEP, this was like n to the 5 halves. And then this previous lifting that was studied in a paper by Werner and one of his collaborators in 2019, they had n squared log n, something like this. But we have now one phase where we think it goes like n to the 3 halves, so it mixes even faster.
Okay.
Compared to previous, yeah. Okay.
I have to move on.
Professor, may I ask a question? Sorry, maybe the time for next talk, right? Okay, just a quick question. Very naive question. Why the steady state corresponding to E equal 1 rather than other real number?
Because it's a stochastic process, because the Hamiltonian is a stochastic matrix, which basically means all the columns add up to 1.
Oh,
that guarantees this.
Okay.
All right.
And do you have a prediction on the root pattern of the base answers for the excited?
Well, I showed you.
I couldn't remember. Sorry. Okay.
So let me just very briefly put this back. So here, share. So it was here. So for example, so play. So in the upper left corner, so that's the root pattern. Yeah, it's some contour in the complex plane. It's a non-trivial contour.
Yeah, the excited state.
This is the first excited state. In the ground state, the steady state, all of these U's go to 1.
I thought this ground state root pattern.
All right.
Sorry. No, this is not the ground state. This is the first excited state.
Excuse me. Okay. It's very hard to chair a session, virtual session, but we have to move on.
I will stop sharing. Yes. Apologies.
Thanks a lot. It was very exciting. Congratulations, and well, let's move on. Thanks again, Esla.
Thank you.
Our next speaker is Juliano Ribeiro from Federal University of São Carlos, which is just across the road. So.
Yeah. So, not yet. Okay, so, let me start. So, today I'm gonna be talking about some kind of statistical mechanics model, and it's kind of honor to be doing that in front of in this event, which is in honor of Chico. And kind of, I mean, the previous speakers had a different take on Chico because most of the time they were working kind of side by side, apart maybe from Fabian, that if I remember correctly, he was already a brilliant advanced PhD student the first time he met Chico. But my take is when I was already I was still undergrad student, and I have the privilege of being in Chico's classroom for 2 years or so. So then, 4 different courses, and I learned a lot of things from him. And he has this special work ethics, and he always pushed people to excel. And this is, I mean, this was very important for me. But at the time, I didn't realize that because, I mean, I was doing experimental physics. So then, okay, I was learning theory from Chico, and then I never thought I would use it. But then, like the students that are sitting here, so the time he and Salinas organized the first school in statistical mechanics after he moved from the Federal University to here. So then they organized this event. And then I decided to attend the school. And that was kind of the turning point for me, where I decided to move from experimental physics to theoretical physics. So in this sense, Chico is the one to blame for me changing, because, I mean, he exposed me to all these interesting things that he was working, and, I mean, everyone else, I mean, the speakers at the time. So in some sense, it was the reason for that, somehow. And then, of course, I had the kind of the minimum background for doing that, because of Chico, because, I mean, I learned a lot from him, already when in undergrad. So in some sense, you never know, I mean, for the students, you never know what you're gonna do in the future. So then you have to take your chances and learn the most, and maybe eventually you'll learn, I mean, you will learn something that you want to use. I mean, from that school 20 years ago, it took me 15 years to use some stuff I learned there or I saw there, then I have to relearn again. So in some sense, I mean, you cannot predict that. So then it's a pleasure to congratulate Chico in this birthday, 7th birthday, and then, okay, thank you for everything. Of course, in behalf of the other, I mean, this is a take from me, but there are many other students who had the privilege to cross Chico. Some of them are not here, so then I congratulate you in behalf of the ones who are not here, yeah? Thank you. So, okay, so the less I talk about Chico the more time I have to talk about physics, but I mean, I had to do that. Then, okay, this is some work I've done in collaboration with Andreas Klamper and Paul Pierce. And the story is, I mean, it's not a, let's say, a straightforward story, because I didn't approach the problem with this in mind. So I didn't want to look at the partition function of the vertex model. So I want to look at the correlation functions of the spin chain. So this was my take at the time. And this comes from, okay, so at some point, across with the problem of correlation functions of these quantum spin chains. And we know that for the XZ, a lot of things are known, so people managed to develop to the full extent analytical calculations for this chain. And then people are spending, I mean, a lot of time, a couple of decades, trying to reproduce part of those results for other symmetries. And then at some point I crossed with this path and I decided to try to take a try on that. And then recently, Andreas Klamper and I, we managed to get some results for the SUN or for the SU3 case. And then later, I pushed these results for the orthogonal model. So in some sense, you think about the Lie algebras A, B, C, E, D. So before people knew results for the XXC, so the A1, we managed to push this to A3, AN, so there's approach developed further. And then B and D, so the orthogonal one, so we managed to get some results. And then at some point I said, okay, we were stuck in the at some point we got stuck, and then we decided to consider the C, which is the symplectic one. And I said, okay, it should be just the same as the orthogonal one, yeah? So in the idea, what is the main idea? Is to avoid algebraic Bethe-Ansatz as much as you can, because I mean, at some point I started trying doing that. But then I gave up. I mean, at least I don't think I could advance using those methods, algebraic methods. So then I started to move to these functional methods. And then I'm going to use these functional methods for this change. So that's the idea. So these functional methods, I mean the quantum cyclic Samolov equations. So, but solving those equations, I mean, obtaining the equations are already complicated, and then solving the equations are even harder. Then you have to do it recursively, yeah? So in some sense, so I I faced some troubles when I considered the symplectic case, and this kind of brought me to what I'm going to talk today. Yeah. So in this sense, what is this vertex model, the symplectic for vertex model? So you can sum up this in an R matrix, and where you have in this R matrix identity, permutation, and this temper-lib operator who already appear in the previous talk, for instance, in Soler. Soler uses explicitly this graphical representation for this object. So, and then they satisfy some algebra, Brauer algebra, and so on. So, and this crossing here is the R matrix, or this is a vertex. And depend, I mean, you can also assign integer numbers, so you have 4 degrees of freedom, so you have numbers 1, 2, 3, 4 to assign to each of these edges of your vertex model, or you can maybe prefer to work with these graphs here. And you have, if you want to do statistical mechanics with those vertex models, this classical 2D vertex model. So what you have to do is to place this in a lattice, so in a square lattice like that. So L columns and M rows, and then each of these crossings is a vertex model. So it means you have these 3 different objects, and so if you sum up all the products and of all these configurations, so then you have the partition function. Yeah. So it is convenient to look at this model in terms of, if you look at a row of this square lattice, and this is the transfer matrix, the row-to-row transfer matrix, right? So it's a product of those R matrix here, yeah? So so in the partition function, you have M of these rows, so as they are all the same, so then you have to raise them to the power M, and then take the trace, and then you have the partition function. Of course, I'm in the torus here, so it's periodic boundary conditions in both directions, yeah? So okay, here we have, so here we have a matrix, and then, again, linear algebra, so it's nice. We can, assume that we can diagonalize the matrix, and there's another assumption. There is the largest eigenvalue is split from the rest of the spectrum, so there is always a leading eigenvalue, which I'm denoted by 0 here. So then, instead of summing all the eigenvalues to the power M, so you can pull this leading one here from the rest, and then makes easier when you take the thermodynamic limit, yeah? So at the end of the day, I want to perform calculations at the thermodynamic limit, yeah? So then in this sense, I introduce what is called the partition function per site. I'm denoting as kappa, it's the same as along the same notation as Baxter does. So kappa, you raise this to the volume 1 over L times M, and then take the limits if both sides goes to infinity. Of course, the limit M goes to infinity is trivial somehow because of the structure, and then you have to do this second limit. And then what I'm going to do next in the next slide. So then, in order to proceed, what is important here? The leading eigenvalue of the transfer matrix. So I don't need to look for the whole spectrum, but the leading one, so which is good thing. So in principle, how can I get the leading eigenvalue? So then, so this is an R matrix, satisfies the Young-Baxter equation, and has some special properties. So this is the Young-Baxter equation. A nice graphical notation, width is inside this, width is the same as this equation. And then, there are some additional properties which we call unitarity and crossing. So these are the properties I'm going to use or going to focus on in order to get results here. So the unitarity has some function here, and then this whole crossing here, and has some crossing parameter rho. So for the case of the symplectic 4, so these functions are well known. So, and the crossing parameter is 3. Yeah. So these are the things I need to know. Before Chico asks, so then I'm going to remind him about the spin chain. Of course, today I'm thinking about the vertex, the classical part, but there's the quantum part. The Hamiltonian is the logarithm derivative of this transfer matrix. Yeah. So in terms of this temper-lib identity permutation, the Hamiltonian looks like that. But if you rewrite in terms of spins, two different kinds of spins, sigma and tau, commuting ones, so you can write Hamiltonian in this way. So and then this can describe some spin orbital model where the taus are are the orbital degrees of freedom. Yeah, so in some sense, this Hamiltonian looks crazy, but it's integrable. Yeah, so we can get exact results for this crazy or kind of crazy Hamiltonian, right? And the quantum, I mean, this model was investigated by Marcio. I mean, the quantum properties is already known. Yeah. So okay, what I want to do? I want to solve this problem to the partition function via some functional methods, via some analytical method. And okay, what was, I mean, developed earlier, I mean, the late 70s, early 80s by Stroganoff, Shankar, and Baxter was what we call inversion relation method. Yeah, so in some sense, the eigenvalues, I mean, all the eigenvalues of the spectrum satisfies an equation like that, where this rho unitarity, rho crossing appear here to the power L, and plus some corrections, which are exponentially small. So it means in the thermodynamic limit, if you raise this to 1 over L, so you will get rid of this power L here, and then you end up with some nice equation for the partition function per site. Yeah? And then with some assumptions again about the analyticity properties of this kappa, then you solve this equation, and then in principle you are done. We have the partition function. And also you can get also the ground state energy of the spin chain as a byproduct of this calculation. Yeah? So then making the usual analyticity assumption, and so in this equation for the symplectic 4 fails. And at least, I mean, I was doing that somehow because doing this correlation function calculation, one of the equations I had to solve is something like that, and then it was failing. Yeah? And the reason, I mean, I'm gonna explain why, but the reason is that this equation is not one equation for one unknown kappa. Actually, I have 2 unknowns in one occasion. Yeah, so in this sense, this equation is not well posed, or it's not enough to solve the problem. Yeah, and the reason for that start with the spectrum of the transfer matrix. Yeah, so then I started to discuss this with Paul at some point, and then we kind of were bouncing, I mean, our heads in the same issues at the time. But at some point we are getting, I mean, the same wrong results. We are agreeing the wrong results. So we get independently wrong results, but they agree. And then we start to look the sources of the mistakes, and then I did some very naive plot, which is the leading eigenvalue. I mean, all the eigenvalues for the largest chain I could, I mean, get analytical expressions easily. This is 4 sites only. So this is the eigenvalues, all the eigenvalues of the transfer matrix. Then I plot it, and then surprisingly, what I expected to be the leading eigenvalues always, this blue curve here, it bends and crosses with some other eigenvalue down there in the middle, and then this somehow brought our attention for the possibility of having zeros of the partition function or the eigenvalues inside the analyticity strip. Yeah, so then, okay, what we did, then we immediately Paul noticed, okay, let's solve let's get the zeros of the eigenvalues that this, I mean, for finite system size, the functions are normalized to be polynomials. Yeah, so in this sense, it's easy to solve, and then we got, okay, this is what we should expect, zeros along the border of the analyticity strip, but then we had some zeros inside or at the middle of the analyticity strip, and they grow linearly with system size. So growing with linearly with system size means that when we take the thermodynamic limit, so this will become dense, and this will become a cut. So in some sense, it's kind of nightmare to deal with. If there are just a few zeros, so we can play tricks, but since they become infinite or a continuous line, so this becomes a blunt cut, and then we have to find ways to complement the equation. Remember, now we have, okay, I know that now, but then I have to find additional equations to complement that. Yeah. and then there's this, I'll show you this later. And then, okay, how can we do that? Okay, the usual trick is playing with fusion. It's like playing with, when you multiply, I mean, the 4-dimensional representation of F4 with the 4-dimensional representation of F4, it splits like 1, 5, and 10. So you can do similar, I mean, the R matrix can be split in similar form like that. So then you can use these projectors to produce additional, higher representations in this thing. So in some sense, you can produce by fusion some R matrix where the auxiliary space is 5-dimensional, and we keep always the quantum space 4-dimensional one. So then this provides us a way to derive what we call transformative fusion relations. And of course, the transfer matrix fusion identity is the first one. This is known since long. Paul Pierce himself has done that. And then we have to complement it with additional functions here. And equations like that also appear when these people develop these off-diagonal Bethe-ansatz. And in that context, these equations are exact equations, but this lambda is not free parameter, but is fixed to some inhomogeneities. Yeah, 12. Yeah, okay. I'm timing. Yeah, okay. And then, okay, so then I have these equations here, yeah? Then, okay, the point here is that I can taking the infinite limit here, L going to infinity, these equations become exact. And then I have 3 equations now, but 3 unknowns. So I have these 2 kappa 4 related with the original problem, and then I have this 5 now in the game. So, but the 5, luckily, has no zeros in the middle of the strip. So then, okay, so then I have only 1 5 and 2 4s to deal with. So 3 equations make is a good deal here. Yeah. So and then technically it's convenient to, instead of solving this, I just solve the logarithm derivative of kappa, which is this omega. The equation looks like that. Then I can solve by Fourier transform, and then. Then the nice thing here, okay, this blue thing that okay, this is a solution in terms of digamma functions or gamma functions, but this blue term here would be the solution if the function was analytic. There are no zeros. That's the solution. This was the thing I was getting before, and these additional terms here are kind of healing the analyticity problem that I had at the middle of the strip. So in some sense, this can be seen as a kind of generalized CDD factors which will correct for the break in the analyticity properties. And but in my case, it's a standard singularity. Yeah, using this CDD context, okay, you have meromorphic functions, so a few zeros scattered. So here I have a line of zeros. Yeah. So then, okay, if you take this function to lambda equals 0, you get exactly the ground state energy, which agrees with the results that Mars obtained by, Bethe-ansatz, plugging the string pattern in the equations and get this solution. So in some sense, we reproduce this. And okay, after integration, I can get finally the kappas. Then I approach the end now. And these are the expressions for the kappas given in terms of gamma functions and also the integration of the log gamma function. And then I could, in order to convince that the result is fine, so then I'm plotting here the result in the thermodynamic limit, so L infinite here, against the results for the finite chains, L equal 8 and 12. So these results are obtained, okay, solution of Bethe-ansatz equations that you can find the Bethe roots in Marcel's paper. You plug in the expression for the transformated, then you plot it. And then you can see the agreement is pretty good. And you can see also here at the middle of the analyticity strip, so you see for any finite value that you can find, you always have some smooth behavior around because you have a finite number of zeros, right? But then only in the thermodynamic limit, this develop a cusp, and this is related to the no analyticity at the center of the strip. So this is for the kappa force, for the object that I was looking for since the beginning. And then, of course, I could also do the plotting for the kappa 5, which is analytic. So in some sense, this was what I was expecting since the beginning. This is what you find for all N models, for the SUN, for the ON. So this is what you find, this kind of behavior. So a leading eigenvalue is always the leading one. So in this case, for the symplectic, you have things like that. Yeah. So, okay, just to sum up. Okay, the result is kind of very subtle calculation because of the analyticity conditions. But once you figure this out, so it becomes a kind of simple thing to do, and you can do this in the thermodynamic limit, and also, you try to compare with these finite size systems, and then the correction factors are we call like generalized CDD factors because they are taking care of this behavior we have at the center of the line, so they're highly non-trivial, so we cannot guess anything like that. But it's a kind of periodic function, so in some sense, in principle, could be possible. Then, okay, what next? I could now go back for the computational correlation functions for this case, but now, since we understand a bit more the problem, we understand that we also, besides the usual QKZ, we have to do fusion in the QKZ, which is kind of unknown, so we have to develop there. So it's still, we learned something, but we still have a lot of things to do. Of course, as a byproduct, we kind of find a way to get rid when we have some breaks in the analyticity properties in the middle of the analyticity strip. So, but this omega 4 function is one of the functions I need, but I need to solve additional equations in the correlation setting. Yeah. So this this is publishing this paper with Andres and Paul. And also, I won't be talking about this, but I also managed to push the result for the general symplectic case, so this can be done, and this was done. And also, there are a couple of other cases where we are analyzing, and there are also this nice feature of breaking the analyticity. It's nice now that I know how to deal with, but then the idea, okay, we can move on to correlation function business, and also we can apply these methods to other chains and kind of deceptional groups. I expect deceptional groups, some of those we're gonna need to deal with techniques like that. And since the dimension is very big, so reasonable to avoid any, diagonalization, things like that. So maybe analytic approaches are more, at least a first try, so to get results for these big models, yeah. So then, okay, so thanks for PSP. This was done when I was in Melbourne, also Wuppertal, and then, yeah, that's it.
Thank you. Questions?
Julian was a student, but although he was experimentalist, at that time he was a very good student. Okay. Julian, remind me a little bit, because I forgot about because you have a prescription that calculates the partition function that will help you maybe in approach to calculate correlation function, so on. But this model, what is you found the critical properties of this? What is this?
You mean the symplectic? You
Yeah,
want to know about? Okay, so I did not have a look at that. This was, Marcio has done that in this paper I mentioned. So
you remember?
So yeah, so in some sense, okay, that's the bit roots. I didn't show earlier, but these are the pattern of bit roots, and you see you have a mixture. These have two bit equations.
Okay.
One of the patterns for the first root, okay, you have real roots and bound states. And these bound states are the one who creates this mess, I would say, because whenever you have bound states, we are seeing these zeros in the middle of the analyticity strip. And so these bound states is the same that contributes for the model to have different sound velocities. I mean, you have excitation, massless, the model is massless, central charge is a product of two tiers of C equal 1, but with different sound velocities.
Mixed velocities.
Yeah, so the velocity is mixed. And the reason, I mean, at least what Marcio wrote in the paper is that the reason comes from exactly from these bound states. So in some sense, the bound states is controlling or dominating the critical properties of the model. Also create some trouble for the analyticity calculations. So in some sense, this must be somehow everywhere. But I still don't have a good explanation for that. I mean, this is the source of the problem. I mean, these bound states usually would have only real roots.
Z for what? Z, no, the dynamic exponent.
Z, yeah. Conform. Yeah.
Okay. So it's set.
Yeah.
We have to move on. So thanks a lot. Next speaker, and the last one of the section, Gerardo Martinez from Rio Grande do Sul.
I thank the organizers for giving the opportunity to present our work. And so we shift to the subject now. We'll talk about Majorana fermions and topological features. This is work done in collaboration with my students, Pedro Wittnich, master student, and Marcos Perez, a former postdoc of my work, of my group. And the motivation of studying the Kita-F model with long-range fading and hoping is the claim in the literature that for long-range interactions, you have a breakdown of the conformal field symmetry for some parameters. But that's the motivation of the group, and today I'm going to study some basic features of the Kita-F, basically to show you how this stuff works now. So to skip some highlight, the first topological system found was the quantum Hall effect, and the quantum Hall effect is these famous plateaus in the resistivity. But basically, in topological materials, what one does is to study continuous deformation of gap states using the Berry phase, or the Zach phase, which is basically the same for translational invariant systems. So quantum Hall effect appears in 2 dimensions, and what I'm interested in is an BDI class, which has a topological invariant of Eisen type Z, where you can find the SS model and the Kita-F also in 1D. So what you do is to shift from the Brillouin zone to the Bloch sphere with this Anderson vector, and the energies are characterized by this D vector. And the D vector counts the number of times the Anderson vector winds the origin. Sorry. So to the point, the Anderson chain is basically these 3 terms. The first term is the chemical potential. The second is a hopping to nearest neighbor. And the third term is fading term to nearest neighbor. This was proposed by Kita-F. And the way to study is you change to the Bogoliubov transformation with the number spin order 2 by 2. You end with a 2 by 2 Hamiltonian of this kind. And you can even rotate the Hamiltonian to write it in anti-diagonal form in terms of, so is finally you write the Hamiltonian is d times sigma, sigma the matrix Pauli. So you work with the eigenvalues and you find that is modulus plus minus d, which has basically two important zeros, closing of the gap. One is k equals 0, which happens at m equals minus t. You can see that at the integrand, if you plug k equals 0, the second term annihilates, and the first one, cosine 1, cosine 0 is 1, so m equals minus t gives you the closing of the gap at k equals 0. And the other is k equals pi, where the closing gap is minus and pi. M equals minus 2t, sorry. So you deal with the eigenvalues, which work the Zach phase, which is the Berry connection down at the left corner, which is basically the derivative of this angle, the theta, the k, and theta is the arctangent of these two elements of the winding vector, dy, arctangent of dy over dx. So what happens is when this winding vector encloses the origin, then the invariant index is different from 0, and you are in the topological range. When on the other side, when the Wilson loop, it doesn't encloses, then the invariant index is 0, and you are out of the topological phase. So finally, you work out all the parameters, and you get the topological phase diagram, which is the left side. And as a function of delta and mu, then the vertical two lines identify the transitions line, the Ising lines. The gray lines are non-topological, ni equals 0, and black and white zones are the topological. So the topological two regions with delta positive and negative gives you induced Majorana borders at the edges. So the diagram is the last one at the right side. What happens is that when the Majoranas appear at the border, the bulk reorganizes, right? So it's written schematically over there. That is what happens when you move from the black to from the gray to the black region. And here you can see, for instance, for 30 sites, what happens is that you see between me minus 2t to 2t, you see some interesting zero energy modes. These are the Majoranas that do not contribute to the energy. This happened because the Majoranas are anti-particles, so they cannot be different from 0. And you have two different symmetries of this spectrum, from positive energies and negative energies because of the pair-hole symmetry. But you also have this symmetry around me equals 0. This is because if you look, I will go back to the Hamiltonian. If you change the unitary transformation Cj into a unitary, which is Cj times minus mu to the power of j, then you see that the first term doesn't change, the second term changes to -1, the third term to -1. So you have the same physics with me positive and negative. So then you understand fully the whole spectrum. So you end up, this is well known, the short range kita model. What I'm going to show you some basic features is what to do with long range interaction. Then you plug in this 1 over L to the power of beta in the hopping term and 1 over L to the power alpha in the pairing term and see what happens. Well, the first thing is you run alpha and beta from 0 to infinity, and you get this winding vector D, and the energies are similar to the previous one, except that you have this sum over cosine Lx, Lk divided by L to the power of beta in the topping term, and the other sine Lk divided by L over alpha in the pairing term, and this changed everything. Well, as a matter of fact, these two terms are related with the polylogarithm function, which is able in Mathematica, so you can work the infinite limit with Mathematica to play what is going on. And the Hamiltonian is transforming this equivalent, this 2 by 2 matrix at the upper side, where f and g are these two functions. The winding vector is written like that, and the energy is, so you can write down the phase diagram. What happens with the phase diagram is very interesting. Now the two lines, the two critical lines at minus 2t and plus 2t, this symmetry of plus positive me and negative me disappear, because you don't have, again, this unitary transformation, so you lose this symmetry. What happens is, this is a different phase diagram. Sorry, now you have in the vertical alpha, and the horizontal axis me over t. But essentially, you don't see, with alpha between 0 and 1, the left transition line disappear. You don't have a transition from the topological to non-topological on the left side. Since the kita short range Hamiltonian is equivalent to the XY model, this should say that you are in that region, you transit from the paramagnetic to ferromagnetic continuously. That's a big stuff. I mean, that's an interesting point, and that was the motivation for starting to work with this model. On the other hand, the claim in the literature is that along these two transitions line, me equals plus 2t and minus 2t as a function of alpha, there is a crossover of kind of Ising type theory to Luttinger type theory. Look, you can see the f and g functions. You have the exponent L to the, on the denominator, L to the power of beta, L to the power of alpha. So the short range kita change, you recover with alpha and beta infinite, right? This is an example with beta going to infinity. The blue and yellow are topological and non-topological. The yellow two regions are non-topological, the blue are topological with n equal 1. But in the cyan region, you have, and the red, you have n equals 1/2 or minus 1/2. This is completely paradoxical. So what is going on? Let me explain why you get half integer results. Because the Zach phase, in this case, you have some discontinuities in the Brillouin zone. So how to deal with this integral d theta decay? At these discontinuities, you go very close to this continuity from the left and from the right, and you sum up all these sums to get these numbers. Then you can explain why you get half-integer values. This is completely non-topological in the sense the classification of topological and non-topological. So we're dealing with this problem. This is work in progress. And the Wilson loops in these regions which you get half-integer numbers are open. So it is really not well described from the point of view of topology. The upper three panels are alpha equals 0, and the lower are alpha equal 1.2, where you recover more or less the phenomena of the K-type with Majoranas. Another subject which happens is when you have finite range, let's say up to second nearest neighbor, k equals 2. You may have up to 2 Majoranas. If you have 3 up to the third neighbor, you can have 3 Majoranas. And the explanation is because the Wilson loops, you can have these 2 rounds. So in the right diagram, you see that precise case, you have 1 Majorana because the loop crosses the origin only one. But if you move the parameter, you can get 2 Majorana because this loop round twice in the same direction, while in the left diagram, you can have only 1 Majorana as you move the parameters. One is with ni equals +1 and the other with ni equals -1. Okay? They are different with different chirality. Now to explain the asymmetry, once you lose the symmetry of mi positive or negative, what you see in the spectrum is that you preserve the n equals 2t closing of the gap, but not in the left, right. So we started with alpha equals 0 some finite studies, and you see we can compare the last level with the polylogarithmic function to study the finite size, and you see the close at the end up to 40 sites, something like 17% of the mass gap, let's say. So basically, the point we have studied up to now with these 2 students, this subject, and this is preparation for the studies of the claim of the literature that we are going to study quantum entanglement with these results and study the entanglement entropy and to study what happens with the central charge as you move with alpha at the transition lines. So with that, I finish. Thank you.
Questions, comments?
Gerardo, do you expect the central charge will change this with this alpha?
I mean, you can plot with finite results, and once you have the entanglement entropy, you can study if you can have some area
from physical grounds. Can you expect from physical grounds? Are you expecting?
Only, well, it's guaranteed only for alpha and beta going to infinity. I don't know what happened. The claim in the literature is that for a particular value of alpha equal 3/2, you change from Ising to Luttinger theory. Because then you simulate with finite size effect only central charge from 1/2 to 1. It changes more or less at 1.5 with alpha. What does it mean? I don't know. But there is a critical point.
Just one observation. when you have long-range hopping and long-range pairing, the dispersion is no longer linear. So conformal field theory doesn't apply anymore.
I'm sorry, could you repeat?
When you have long-range hopping, the dispersion is no longer linear.
Yes.
And conformal field theory doesn't apply.
For the moment, we say that basically long range in the pairing, not in the hopping. Yeah.
But it should be the same, I suppose.
But I expect some abnormalities.
You probably get the volume law for the entanglement instead of area law.
I have no guess. No, I don't know.
Hi, I have two questions. First, I didn't understand the two Majoranas. So you have the two Majoranas in the same edge, in same side of the chain, in the last.
I didn't get.
I didn't understand the two Majorana limit. So what is the two Majoranas? So you have the two Majoranas in the same side, in the same edge. I think it's 2 or 3 transparencies. Yeah. No, I think it's
here.
A little bit. I think
this,
further a little bit.
Sorry, this is a diagram for beta equal infinity.
Yeah, it's a couple of slides ahead. Yeah.
Further.
Yeah, further.
You plot against the
next one. Yeah. So I didn't understand what did you mean by two Majoranas there? So do you have the same
with
two Majoranas in the same
beta
edge?
equals 0, and you are within the topological region.
So, but the two Majoranas are in the same side, in the same edge?
Sorry?
So the two Majoranas are in the edge of the chain, in the same edge? The two Majoranas, you said that you have two Majoranas.
Yeah, you can put the origin in this.
So, but they are in the edge of the chain, in the same side, or because usually you have one Majorana in each end, right?
Yeah.
So now you say, well, and you have this long-range hopping, long-range pairing, you can have two Majoranas on the edge, but it's the same edge. I didn't understand.
This is the infinite case. We took the polylogarithmic function, so I cannot see the borders.
Okay. So where do the Majoranas live?
To get the Majoranas at the border, I have to calculate with open boundary conditions for finite size. This is infinite number of sides.
The other thing is another question, is simple question. So usually in the Ising model, you have a very clear power law where you go from local behavior, local interactions to long range, right?
For the correlation function, you mean?
Yeah, for 1 over
R
squared.
I haven't calculated the correlation functions yet.
Yeah, but 1 over R squared, right, is the separation between long range and short range physics in the Ising model. So in the Skitaev chain, do you have something like that when you introduce the pairing? Do you have a clear power law where you have a change in behavior? Because you calculated for beta and the power laws.
Yeah, right.
So do you have a clear change in behavior for a particular value of beta or a power law that will say that, well, if it's slower than 1 over R squared or faster than 1 over R squared, do you have a change?
What I guess is that if you calculate correlation functions, you maybe will have exponential behavior change into algebraic as a function of size, I guess.
All right, thank you.
All right, no further questions. Let's thank Gerardo again.
Okay.
There will be a dinner at the end of the workshop in this Cachaça House place. It's a very good food and very nice drinks. If you want to join, you need to send me an email so I can do the reservation. So if you're going to come, please do send. It will be tomorrow, 8. Yeah, around that time. And let me know, because I need to do the reservations. We resume at 2 p.m. as scheduled.
Não conseguia. Finalmente.